So right. And so spin, right. Okay, the arrows. So that's actually that's that spin, that arrow that you're drawing, the up and the down. Those are the magnetic fields for the. Oh crap! Where did I put my pen? Those are the magnetic fields for the spin of the electron. So when the when the electron is spinning like this, it has an up spin. That's the direction of the magnetic. Yeah, it's related. Yep, the angular momentum. Exactly. And then if it's spinning like this, the magnetic field is going to be right. So the magnetic field this way. They're in opposite directions. This is why an up spin and a down spin cancel themselves out, right? When you're doing those things you were talking about, these cancel themselves out, right? And then if you're left with one up spin, that's essentially telling you you have one electron. And that's true because there's not a paired electron with it, because the paired electron will have the opposite spin of the electron that it's paired with. So you know how it's kind of a chemistry thing. Some of you I know are not even in science, but electrons kind of pair up around the orbitals based off the type of orbital. The first one just has two, but then after that, they kind of like to pair up. And so when they pair up, their spins are opposite. Anyway, I'm digressing. But just know, this is just like I said, the point of this, he's not going to test you on it. Just make sure you understand, because we're talking about it, right? Like if I asked you, well, where does electric fields come from? What would you tell me? You need to know for this test, but where do electric fields come from?
From electric charges.
Yeah, it's that simple. I know it sounds silly, but or simple or but exact. That's 100% correct. It's just charge. Electric field comes from charge, a negative electric field and a positive electric field, right? Or literally, or I shouldn't say positive. Well, yes, it's all about direction, right? Electrons have an inward electric field. Positive charges have an outward electric field, right? And so it's simply just because they're charged. They don't have to be doing anything. So you should just know in the back of your head that, oh, okay, if someone comes up to you and says, okay, you just told me where electric field comes from, where's magnetic field come from? What would you tell them? It's simple, just as simple. Where does it come from?
When those charges are moving.
Boom. That's the answer. If they say go deeper, say, well, we're going to have to talk about quantum mechanics. And then they'll be like, oh, that's okay. but yes. Okay, that's exactly. And like I said, I think I told you I got taught how to teach physics. And so my mentor who taught me, when he talks about, because spin is the fundamental source of magnetic fields, right? The spin of the electrons. You can kind of think of charge and spin, both of those two things, as DNA. Okay, that's the best. So that the charge and the spin of an electron, that's what like makes it an electron. Because other particles have different charges and different spins. Maybe they might have both negative charge, but they're not going to have the same value. Like electrons have a very specific charge and a very specific spin. And that's their DNA. That's what makes it. So if we wanted to look at a proton has a specific charge and a specific spin. And that's what makes it a proton. Okay, so that's the idea. Let's move forward. So when we have these magnetic fields that are there due to all the types of sources we were talking about, could be a magnet. And yes, he went through the different types of types of magnetism we can have. I don't think he asked you any questions on those, so we don't really need to go through those in detail, but no, there's different types of ways to generate, or there's different types of materials and different types, and the way that they become magnetic could be, there's different ways to make materials magnetic. You can run a charge through them, right? That's what we call electromagnet, like the object might not have any magnetic field at all, like, and then we run a charge through it and it gets a magnetic field from the current, right? So we can make one, or the object can just be naturally have a natural magnetic field, like you've seen with iron and things like this. Okay, so when we have another charge moving in one of those external, and so what, I guess we can use these words, right? Because we're going to be using them over and over. Essentially, this thing that we were talking about from the very, 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 very beginning is, I'm going to start calling it be original. And that's what we've been calling it in class, right? Even though at the beginning, when we started talking about this, we didn't say this word yet. But now you know this word, right? And you know how important it is. And that's what this was. Okay, there was a be original, which means that there's a magnetic field present from something. Okay, and then when we send another charge through this thing, right, that magnetic field will apply a force to this charge. Okay, and that's all this first thing's trying to talk about. And this is very specific to just charge. Because there's another one, right, written, I mean, it's the same equation, but there's another, I like to separate them for you because I found that helps you all to learn them, rather than us physicists, we keep telling you they're the same thing, and you all like, great, they're the same thing, but I sure as heck don't use them in the same place, so stop telling me they're the same thing. And you know what, you're right. So I'm going to talk about it as it's different, right? But we know that we have a magnetic force equation for just an individual charge, which is what this is. And then we have a magnetic force equation, right, that's for current running through wire. Another way to say that, right? And this is the, we'll come back to that here in a second. So, right, but they're both just trying to describe the same thing, which is magnetic force. All right. One question here real quick. This charge, I said it was moving, right? Like that way, right? To the right. Does everyone see that it's moving? So since that charge is moving, what does that mean it has? Good job. Yeah. See, that's where it comes from. So we're not talking about it. You actually have to take a way higher level physics class to start talking about the thing I'm going to talk about. But what actually where this force comes from is actually this magnetic field interacting with the magnetic field on this charge. They interact, and then it causes a force on the charge because of the interacting magnetic fields. That's actually what's happening. But we can't talk about that in this class, but that's the idea. So when we have, right, we talk about two different types of charges in here. And also remember, these don't have to be protons and electrons, okay? Like if this was a current, then these would definitely be moving in the opposite direction, right? But if this is like your blood, for example, then these charges are going to be moving in the same direction, right? So we're just going to use this to demonstrate everything. But keep in mind, pay attention to your system. I mean, we're going to talk about it here in a second, but pay attention to your system, right? Charges can be moving in the same direction. You can go ahead and just ask your questions. I love hearing them, and we're very casual in here, and just we're trying to have fun. So go ahead.
Thank you. I was wondering if the X's that are in black are the be original, and that's a magnetic field that was present from the start, and our moving charge with a velocity creates a magnetic field. Are there two different magnetic fields interacting with each other?
Mm-hmm. That's exactly what's happening. And those two magnetic fields, when they interact with each other, they cause a force on this charge. That's where the force comes from. So, you know, this is the thing with the algebra based, is that you don't see, like we taught, and we can do a lot of stuff in here. but it's hard to see the fundamentals. And so I think I told you last semester that force isn't something that the universe actually understands. The universe doesn't talk in terms of force. The universe only talks in terms of energy and momentum. And where do we see energy and momentum here? Momentum's in the particle, but the energy's coming from the fields. And so, and force is actually, believe it or not, something just called when we do the gradient of a field, we get force. That's really all force is the gradient of a field. But we can't talk about that in here neither. But it's a thing, and it's fun and cool. Anyway, so these two charges, right, when they move to the right, they're going to have a force applied to them, right? So let's start with the positive charge. Now, this is the right-hand rule. So I see it a little bit different than Dr. Ngana, but we're saying the same thing. Okay, so the first, and most of you should know this, but let's practice this, because just because we know it doesn't mean we don't need practice on it, right? I always need practice on it. So the right-hand rule, right? First, we want to put our hand in the direction of V. Oh, you know what's better? I usually label it up here, and I should just do that. Well, I'll put it in both places. So this is hand direction. Okay. And you want to do it with your finger. So like extend your, like, so in this case, V's to the right, right? So you want to extend your fingers in that direction, like 4 of them, and then make sure that your thumb is actually like as perpendicular as it can be to your pointer finger. So that's what your hand should look like at the very beginning when your hand's in the direction of V. Does that make sense what I'm saying? Do you see it, how it's I mean, I can't draw a hand, but do you see how that's the attempt of a hand? Okay. So that's how, that's it. And this is true for all of them, okay? Like we're always going to actually start like this with our fingers in the direction and our thumb perpendicular. It's actually all of them. And then, and then what we're going to do is, I say palm direction, but we in class, we call that finger curl direction. But the best thing to do is then put your palm, because you can't, and Dr. Ngana was saying this, you can't curl your fingers in the opposite direction of your palm, okay? So you want your palm in the direction of B. And in this, it's always, right, this is like, this, in this case, we're talking about like B original, right, which would be this. Well, there's not another one here. All right. So, and then what you can do is if your hand, and don't change your thumb, keep your thumb perpendicular, your fingers in the direction of V, and then your palm should be in this case, and our RB is into the board. So your palm, if we're going to use this as an example, your palm should be into the board or into the screen, sorry. All right. With your thumb pointed up to the top of the screen and your fingers to the, like pointed to the right of your screen. All right. And if you have this already, your thumb is actually already in the direction it needs to be. Okay. Your thumb's in the direction of force. It's where it should be. But very lightly curl your fingers, because that is what we want to follow the rules here. And wherever your thumb's pointed is going to be the direction of force. But like I said, if you're starting with your hand like this, right, and then you move your, keep your palm, keep your hand like this as you orient your palm, like never take your hand out of this orientation as you orient your palm, then your thumb will already be in the direction of FB. And then you can lightly curl your hand if you want to, but you necessarily don't need to. Your thumb is going to be where it should be already. All right. Cool beans, everyone good? Cool. Okay, I thought I saw a question. No. Okay, great. All right. So for the positive charge, yeah, you can call it right-hand rule number 1. What I like to say to you all, so that they're really, 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 really stuck in your head separately, because they should be, is I like to call this the right-hand rule for an individual charge. Okay, because what we're going to do, even though, yes, they are the same way, I know, this to, and you'll have them completely separate in your head, then this is the magnetic force for a current going through a wire, right? Because they are used, I mean, they really are used separately. Like when we're doing induction, at first you're using this FB, right? This FB that we're talking about right now is the one that gets you the direction of how the charges are going to separate, right? And then this FB comes from when there's a current flowing through that wire, if it's going to like affect anything else around it, right? But does that make sense? So it's, even though we keep saying they're the same equation and stuff, they're describing two different things. And so rather than call them one or two or things like this, like it's like, let's just call them what it is, right? So this is the right hand rule for like an individual charge. And you could even go as far as to say the right hand rule for magnetic force, because we have two magnetic force right hand rules, right? Which is the one for an individual charge and the one for current going through a wire. And then we have two right hand rules for magnetic field. Those other two are for magnetic field direction. And so, you know, to even, you know, to even go as far as to say this is the right hand rule for the mag force might even be super helpful as well, like the right hand rule for mag force on an individual charge, because that's really what this is. Okay, so our thumbs pointed in what direction for, if we've done this correct? I think the picture's actually showing. I would have switched. So if your palm's facing the screen, your fingers are to the right. Your palm should be facing the screen because B is in, right? Thumb should be up. Good. So the direction of force is going to be, whoa, up. I want to move it over so I can draw that. Good job. And then we know that for the negative charge, all we have to do is what? Now, if all you have to do is, if all that's there's a negative charge, you have to go through this whole process. But since we have this positive charge here and our hand is already in a specific orientation, right, with our thumb up and our fingers to the right, what do we have to do for the to get the magnetic force for the electron? Yeah, we just have to flip our thumb in the opposite direction. But remember that if there's no positive charge, make sure that you do all this, and then just remember the caveat that is, you know, for negative charge, you know, flip up when you're, you know, after you've done step 3. Okay, so in this case, right, if we start at the beginning, our fingers would be to the right, palm would be facing into the screen, thumb would be up, right? And so what we'd want to do is, if you'd like, curl your fingers in, thumb should still be pointing up towards the top of the screen, and then you want to point it downward, right? Just flip it, literally flip it in the, literally flip it in the opposite direction. Okay, so those are the magnetic forces on individual charts. Cool? Everyone cool with that? So, and yes, in different chapters, we did some jumping around, but let's just look at the application of this really, really quick. Okay, because we showed you this and we did other things and we came back to it. That's what I mean, like, you know, see it all together. So what are the two major applications that Dr. Dungan is wanting you to pay attention to here? Well, the first one would be for like some kind of, I mean, there's you know, cyclotrons, they're different names, but they all work the same. Mass spec, right? Those are still just a magnetic field that we're spinning things. So they're all different. I don't know what word he's going to use, but either way, the science is the same. You'll see what I'm talking about, that, you know, they're all fundamentally built the same way, where we're essentially sending charges, pushing charges through a magnetic field. Okay? And when we push those charges through a magnetic field, they're going to have a force, you know, applied to them. So, and when that force is applied to them, I guess the important part here, this is the thing to focus on, is whether it's a mass spec or a cyclotron. When that force is applied to that charge, it's going to make that charge move. How? You should know this already. Like for a cyclotron or a mag, like I shouldn't even say it, for any one of those things, or if there's just a constant magnetic field, right? Just this magnetic field goes on forever, right? And it's everywhere. It's literally everywhere. I don't want to spend time drawing it, but it's literally everywhere everywhere. What's that going to cause the charge to do? What type of motion? Yeah, either charge, positive or negative. Right. There we go. Like there, like we call it rotational, but yep, you all are saying the same thing, which is perfect. Okay, the particles move in a circle. So what's the big takeaway here? First, before we write that, is that you need to make sure, right, that you understand in your head that electric fields. This is the big takeaway, right? They make charges move. I, I hate to say translational because we can't. Electric field can make a charge move in a circle, but that electric field has to also be changing direction, right? The charges follow the electric field, right? And electric fields themselves, when we saw them, right, like in one, if like this electric field here, right, it's in one specific direction, just keeps going this way. So if I put a charge here, it would just follow it in that direction, right? The only way that charge would be able to move is if like that electric field went away and then all of a sudden like a new there's another like positive charge here, right? So once this positive charge got here, that electric field wasn't there anymore, but this new one's there. So now that positive charge is going to move this way, right? So electric fields can make, right, and that would cause this positive charge to have a little bit of circular motion right there, right? Because it was moving to the right and now it's moving up. So electric fields can cause this, right? But overall, we like you to have in your head that, charges follow the electric field. So essentially, the charges will electric fields give charges translational motion, but essentially they follow the direction of electric field, right? And then the magnetic fields, just call it B, they make charges move, give charges circular motion, right? All right. So, okay. So if I send a charge through here, and it doesn't matter which one. I'm just doing positive. Okay, we could totally do negative here, but let's just say I send a positive charge through here. First of all, where's the force going to be on it right when it enters? Good. And it's only right when it enters, right? Because what's going to happen, like literally the second that this charge gets in there, what's going to happen? That force is going to be there, right? That force is technically like here and here, right? As the charge, moves to, right? It's there. So it wouldn't be moving in a straight line, or having translational motion with that force always there, right? So maybe it might be more appropriate to say, this charge would be here. The minute that it gets in that magnetic field, it's going to feel a magnetic force up. And if you're not sure how, let's just do the right-hand rule, right? So if this charge is moving to the right, our finger should be to the right. The B field, I should have done a different direction here. I apologize, but the B field is still, it's like the last time, it's into the screen, right? So our palm should be faced into the screen. And if you're doing it correctly, right, with your fingers this way and your thumb perpendicular to your fingers, then your thumb's already in the appropriate direction, but give your fingers a curl. And when you do that, you see that FB is up. Everyone cool beans with that? All right. And so because of that, like the minute it gets in here, it's going to make it start moving in a circle, right? And so that the reason why I say the FB is only up at the beginning is because, when it's here, I mean, you all know this, right? The force, if this is moving in a circular fashion, which way should the force always be? Exactly. Can any of you confirm these directions with the right hand rule, test it out. So like right here, right, the velocity being that direction, right here, test it out. See if you get the force towards the center of motion using that direction of velocity that I'm giving you. You can use either, no matter which particle you want. But follow the right hand rule. I'm going to let you do it on your own, and then we'll do it together. But are you getting that force no matter where this particle's at towards the center? Yeah, it works, huh? Cool beans, huh? So and that's awesome. Great. And so yeah, and so that's where the circular motion is coming from, right? So let's like for example, some of these are kind of in a weird direction, but okay, let's do this one. So let me make it a little bit more clear. So your fingers should be pointed in that direction. Okay, and then your thumb, just because of the way we're doing this, just automatically be perpendicular to your fingers, right? Now put your palm, I don't think your fingers would be able to be in that direction if your palm wasn't facing in, but, well, no, I guess it could, but your hand would be twisted weird. So make sure your palms face the screen. And so your thumb, if your fingers are pointed in this direction, hold on, I'm getting a question. So I'm getting a question asking, and it's not a dumb question, but is force going to be like perpendicular to velocity in the case of a moving charge? Yeah, exactly. Like there, and that's the whole thing. That's essentially what this equation is. See, this equation, it's this fundamental idea is a cross product. And so I'm gonna talk. We don't. The one thing the only reason why I want to talk about this is because there's just one thing that we need to understand because of the cross product, and because this is fundamentally a cross product, the FB. That means that these three, the three vectors in here, right? V is a vector, B is a vector, and FB is a vector. And keep in mind, the other cross product you've seen before is torque, and this is also true here. That this vector, and this vector, okay? These three vectors are because when we use a cross product, they're all perpendicular. They're all going to end up perpendicular to themselves. So V is going to be perpendicular to B. B is going to be perpendicular to FB, and FB is going to be perpendicular to all three. They're all going to be perpendicular to all three of each other. Just like torque is perpendicular to F and perpendicular to R. And that's why you can use the trick. This is why this is the important part here. This is why you can use the trick that if you're looking at a question, so like in this case, right, let's just start with a simple situation with at the beginning, the velocity was this way, right? So you knew the velocity was in the X direction. You knew that the magnetic field was in the Z direction, it was into the board. So because of this and because of the cross product, all the three values in there all being perpendicular to each other, you already knew before you even started to do the right hand rule that FB better be in the Y, because these three things have to be perpendicular. That looks like Y and that's supposed to be X. These three things need to be perpendicular to themselves. So if you know the direction of B and you know the direction of V, you know the direction of FB. Your only job now is to get positive or negative. Like this won't tell you positive or negative. You need to go through the right hand rule, get positive, negative. But the one thing you can do is use this as a check, is that if you're doing the right hand rule and you know like your V is in the X direction and your B is in the Z, and you're getting FB in the X direction, that can't be, you can check yourself and be like, that can't be right, because I know VB and FB are all perpendicular. If one of them's in one of the plane and the other's in the other, then that means there's only one plane for the last vector to be left in. Does that make sense what I'm saying? You can use that to check yourself on every problem. You can say, is everything perpendicular? Because they need to be. That's like a fundamental thing. So we never said this, but the dot product, when you use the dot product, what that mathematics allows you to do is it just lets you see how in line those two vectors are that you're using in the dot product. Here for the cross product, what this mathematics allows you to do is it's allowing us to look at how perpendicular these two vectors are to what. That's essentially what this answer is. But that's mathematically what it does. Okay, so because this is moving in a circle, right? We can write an equation for it. What's the equation we can write? Because this thing has circular motion. I know it's kind of messy. I was trying to prove a point. There's all kinds of mess on here. And we're trying to do mathematics. That doesn't help anything. So we know it's moving in a circle. So what does that mean? You know that what law, and remember, we're doing normal physics here. So you always want to start with like free body diagrams and Newton laws. That's where you always start. We essentially got our the one thing we're missing that we could probably put here, because again, the only reason we can put this here is because we know this thing's moving in a circle. We should put that radial acceleration there. But outside of that, everything else is good. Yep, circumference and radius apply, but we should really be thinking about new and keep in mind, this is a general rule of thumb. It's not because of this question that we're doing this. Remember, every question now for the rest of the semester, this isn't going to be true, but for this stuff we're doing some different stuff for the rest of the semester. But for this stuff, the real hardcore stuff that we've been doing, any hardcore physics, we always start with Newton laws. Believe it or not, the quantum mechanics equations are actually forms of Newton laws. But yes, Newton's second law. So, and again, we know we need to start there. Why? Because this particle is having a change in motion. The only law that connects net force to circular motion is going to be Newton's second law. That's how you should be thinking. Because remember, Newton's laws only do one thing for you. They connect net force to motion. They do not describe force. Okay, force describes force. If we want to know what tension is, that's a different ball game than this. Newton laws are trying to their only tools connect force to motion, net force to motion. So this thing's having a rate of change in motion, which we know that's what acceleration is. That's how we know we got to start here. A lot of ways you can think there. All right, and then what we have our free body diagram here. What forces? What forces do I put on this side? Right. So we have our free body diagram. So it's telling us there's only one force there, right? Which is good. Okay? This is just like last semester, right? There's only one force there, and it's FB. And the other thing, I should have done it up here, but because we're moving in a circle, right? We need to make sure that this isn't just acceleration, but it's radial acceleration, because it's not translational. And so in these cases, and Dr. Dungana can totally have you do omega or tangential velocity here, but Dr. Dungana does tangential velocity here every time. And so we essentially want to be able to solve for the speed of this particle, the velocity of the particle. We can solve for different things, but that's typically what he's wanting you to do in these situations. And that's the question he gave you on the lecture slides. So, and we know FB is equal to QV B. Now remember, you want to use this equation if you have to do the mathematics. All right, don't use QV cross B, because if there's some freaky angle or something going on, you'll never be able to do it in here, right? Always start here. Get rid of your sine theta and then move forward, just like you did with the dot product. Remember when we would do work, we'd always take care of cosine theta first? You remember doing that? It's the same thing here. So write this down. Always take care of this part first. All right, and then everything else will come into play. So let's do that first before we put these together. So what is sine theta here? Remember, this works no different than before. Like cross products and dot products work the same. This is always the angle between V and B. Beautiful. And so sine 90 is 1, right? So it essentially just drops off. We'll never be dealing with the 270, okay? So it's either sine 90 or sine 0 or sometimes sine 180. But sine 180 and sine 0 are both what? What is sine, at least sine 0? What's that? Good. And then sine 180 is also 0, right? So it's either going to be one of those two things. Dr. Dungana doesn't do anything outside of that for you. So there we go. All right. So that means that sine theta essentially just like kind of drops off, right? So the FB that we're going to be using for our math here is just going to be this. So we got QVB is equal to now MAR. That AR, I forgot to finish up saying what I was saying there. So since Dr. Ungana will always be just asking you to solve for tangential velocity, that's also why we know we'll only be using like that conversion of AR in this equation. Because if some of you are like, what are you talking about, Carl? There's another way to write radial acceleration, which is like this, using omega. Okay, but Dr. Ungana always uses this one. That's what I'm trying to say. And then, so then we got this equation. Cool. Now remember, like remember, first of all, in physics, well, there's one more thing we can do before I say what I'm going to say. There is one. I mean, no matter what's going on, you're gonna always do this. What's the yeah. Because these will, right, because of their relationship, like no matter what you solve for, even if you solve for v, they're gonna cancel, right? So let's get rid of those, and then now I'll say what I was gonna say, which is remember when you get I just put so we had this FB is equal to MAR, and I just popped that in there, and then that got this. Does that make sense? Awesome. So remember with these fundamental equations, okay? Like Dr. Ungana typically has you solve for V, but you can solve this thing for anything, okay? B, Q, R, M, all of them, okay? In fact, because remember, this is the same equation for a mass spec. They might ask you, like they might give you the speed and say like, what's the mass of that particle? So you could use this equation to solve for mass, right? So you can do a lot with this equation, but typically Dr. Ungana has you solve for velocity. So that's what we're going to do. Like I said, that's the question. How do we know that? Is because we pay, if you look at his lecture slides, he doesn't have you do anything else with this equation. So that's why we can say that. It's like, Carl, how do you know that's all he does? Well, look at his lecture slides. He never uses omega. And so that's how you should be guiding yourself to study for his test, is by saying, oh, Dr. Ungana doesn't do that, so I don't need to worry about it. Does that make sense? Am I doing this right? Yes. I'm talking while I'm trying to do that. All right, cool. So that's cool. Okay. All right. And then the second place that he really wants you to just understand here, and it's the same thing, but this is really more concept, is just that thing with the blood. And the only reason why we want you to understand this, I don't know, he asks you a lot of questions, but why is this like the important part right now in terms of what we're still just trying to talk about FB on the charge, is because this is a form of induction. We didn't say it yet when we first did this, but it is a form of induction, right? Because if I have these two charges in, well, there's multiple, like a ton of charges in our blood, right? But right, so there's a ton of charges here. They're going to set up, but we're just going to talk about, two at a time. And this is in my blood, so they're both moving this way, right? In the same direction. And then I apply a magnetic field I don't know, it's not there before, right? And then I applied this magnetic field to my blood, which would be the original. Okay. And then what happens to these charges? When they, because they're all going to flow into this, and this magnetic field's everywhere. Okay. I'm not going to draw it, it's everywhere. It goes all the way down. I'm not going to spend that time though. Yeah. And how do they separate? So the positive charge is going to be here. And again, the magnetic field is all the way through. Negative charge is going to go through here. Do our right hand rule. So first of all, no matter which one, our hand needs to be pointed. Fingers need to be pointed to the right. Thumb perpendicular. Okay. And then I should have done the magnetic field. Why do I keep doing it in? Okay. So palm should be faced in. Okay. And fingers pointed to the right, thumb pointed up to the top of the screen. Now lightly curl your fingers if you'd like, but your thumb should be pointed up. And what is that the force for? The positive or the negative? Good. And then for the negative charge, if you want to, you can go through that whole process again, or you can just do what to save some time? Yeah. And you can say, oh, if that's for the positive, like that's a concept, right? That's like something you can remember. Like you should memorize that and part of the reason also is because that's something similar that the magnetic force has with the electric force, right? For electric force, the force on a negative charge, right, in an electric field is going to be in the opposite direction of the positive charge, right? Just like we see here, right? So it's something that they share, right? They have opposite forces on them when they're in the magnetic, same exact electric field, and it's true for the magnetic field that when two charges have the same magnetic field applied to them, two opposite charges, they're going to have an opposite force applied to them. They're going to go in opposite directions. Okay, and so when this happens, what do we induce? Remember, there's a ton of charges. These are the first two, but let's say there's like hundreds of charges, right? Because there are flowing through your blood. They're going to start to separate and do what? They induce a what? Yeah, exactly. Right. So here was our first example of where we see magnetic fields inducing electric fields. Right? It's something that happens, right? This electric field wasn't there. And if we take the magnetic field away, does this electric field stay there? No. The magnetic field literally induces it. It's there only because the magnetic field's there. Right? So yeah. So that's what's going on here. And then what happens, so I'm going to just tell you the rest of the story because we got to move forward. And Dr. Montgomery, like I said, he's more worried about knowing this right hand rule to get to this situation here. Okay. But then once we get to this point, I mean, he might ask you what I'm about to say, but the, you should already know this. So what direction is let me just ask you though, just to make sure, what's the direction of the electric force on the positive charge? So we know FB is up for this thing, but what's the direction of the electric force? Good, because the electric force is always in the same direction as the magnetic field. Good job. And then for the negative charge, right, we said FB was down, but then for the electric force, which way is it for the negative charge? Opposite. Yep. Good job. So what we've actually done here, it's called Hall voltage. So we take advantage of this in our blood, and that's what we're doing here. But it actually came from electronics and things like this. But see right here, we have this electric field, right? And this electric field has a voltage to it. And that's something that we call a Hall voltage. So, we apply a magnetic field to our blood. What happens is that the charges will separate, but the amount of charge that separates is only going to be based off the strength of the magnetic field that's there. So eventually, charges are going to stop being affected by the magnetic field as this electric field gets induced more and more and more. And then what happens is that those two things end up balancing each other. Like the strength of the magnetic field, because it's inducing the electric field, the magnetic field ends up dictating the strength of the electric field. And so they end up balancing themselves after, a few minutes. And then the rest of the charges are just going to flow through here with a constant velocity. And so we can do a lot of stuff with those charges, like absolutely, we can do that. Non-stick glucose meters. So like we'll do this, and then glucose has a certain charge to it, right? So like we don't have to get your blood anymore, because this thing's going to have this charge to it, and then we know that charge, and so we set up the thing to say, hey, pick up on this charge, and then we know like how much glucose is flowing through your blood at that particular time, and that gives us your blood, your glucose level, just by doing that. Yeah, there's a lot of cool things like in terms of medicine that this applies to. But yeah, and so because of what I just said, these things become balanced. We should know that Newton's first law is going to be applied here, right? Like I said, the Fe is going to be equal to the Fb. No. So what happens is this magnetic field will cause a certain amount of charge based off the strength of this magnetic field to start to separate. And as those charges start to separate based off the strength of the magnetic field, this electric field is going to start to be induced because of the electric field being induced. And so their strengths end up balancing each other. So there's going to be a certain amount of charge that separates and causes the electric field, but then there's going to be remaining charges that are just going to be still just moving through the blood, but this velocity is going to be constant. This is also something like in physics, we call this a velocity selector. And the reason why we call this a velocity selector is because we can literally set up the strength of the magnetic field, which we know the charges we're trying to send through it. And then we can say, I want this charge moving at this specific speed. Like I need my electron to move this fast if it's going to do the thing that I want it to. So what I do is I need to shove it through a velocity selector, which is essentially, I set up the magnetic field, and then I also set up the electric field. Like the electric field isn't induced in this case. Like we actually build it so that I'm directly like getting the velocity that I want these charges to be at. So I set up this situation, we set up these situations like this, and then the charge that we send through here is going to move at a constant velocity because there's this electric field and magnetic field here that are essentially causing this balance in force. And then we can choose the speed that we want. So there's remaining charges that are moving through here. Charges remain to move through here, but not all the charges. And we can actually select the ones that we want, essentially. Or we can, like I said, with like the glucose meter, we can like put in the glucose meter like the charge of glucose, and so it'll measure that, because glucose is huge, right? So it's the smaller particles that are going to induce the electric field. It's going to be hard to push glucose, but glucose will definitely be one of the molecules that's still going to be moving because it's so big through your blood after this electric field induces. And so we can see how much of it's in your blood. So when these are balanced, we know that the Fe is going to be, well, they're balanced in an opposite direction, right? So if we assume that, let me clear some stuff. So, right, if we assume that, and we'll just use a negative charge here, Fe is up, then Fb is down, and down is negative. So that's going to be negative. That's why I'm writing it this way. That's going to be equal to 0. And then here we know Fe is equal to E times Q, and Fb FB is going to be equal. Now here again, we'd want to definitely start with this, but everything's 90 degrees to themselves again. So we know this just turns into 1. So this is the FB we're going to be using for this equation. So let me get EQ. Now again, this is the fundamental equation. There's no reason to solve this thing any further unless you need to, right? But it ends up being one of the equations you're actually using right now, that you just got done using for electromagnetic radiation. But when we solve this thing for V, right, we see the Q's cancel out. It's going to be V times B. Like I said, we're trying to solve this for V. So V is equal to E over B, which is the electric field over the magnetic field. This is also the equation. You should know, this equation should look very familiar because it's also the equation for what? Does anyone know? The speed of light. Okay, so the speed of light is equal to E. And that's, anyway. Those are the two things he wants you to know. Those are the things he really focused on in terms of FB directly. So is everyone good there? Like I said, for this one, he's more focused on you just practicing the right-hand rule. But this one, I think he wants you to know the math, okay? Because circular motion, you should, I'm almost for sure he asks a question like this on the test, okay, for the circular motion. All right, so now this one, right? So that was individual charge. So now what about when we run current through a wire? Well, it can, right? It'll also produce, right, a magnetic force, right? If there's a magnetic field present and that wire is sitting in that magnetic field, then it'll produce a magnetic force on that wire, right? Sorry, I couldn't say that at first. I knew what I wanted to say, but the words wouldn't come out. I don't know why. And that's what this is trying to say, right? So this is, again, like some sort of be original. And again, just like over here, remember, it's easy to think about over here that we said, okay, well, the original magnetic field is just coming from another magnet, or it could be coming from another wire. But that's what we have to think. So if I have another wire that's sitting, yeah, it makes sense. Oh, there's just this magnetic field here. Okay. Yes. Magnetic field present. This wire with a current is running, is in it. So there's going to be a force on this wire. But where we tend to see some confusion is when we say, okay, well, this wire is sitting next to another wire. And what do we know about this situation? Not only, and we kind of talked about it at the very beginning, I've already mentioned it, but what do these, let me ask you this. I should have asked this better. What do we know that individually a wire has on it? Like when a current's running through a wire, what do we know it has? It has a property. What property does it have? Yes, it generates its own magnetic field. Exactly. So when we put, like I said, we mentioned this already, just saying it one more time. I mean, it's an important thing. So when we put two wires next to each other, their own magnetic fields are what start to affect each other, right? Like this, like let's say this is I1, right? And we'll go through the right-hand rules here, don't worry. But this would be going in and out here. I1, this would be B1, the magnetic field for I1, right? This magnetic field cannot affect I1. It'd be like picking yourself up, right? This wire has to fill some outside source, not its own source. Just like over here, it makes sense here. It's like, okay, well, this is the outside source. This thing sitting in it, it's going to fill a force. But when we threw in the idea of like, oh, no, but now, right, because we first just talked about force. And then after that, in the next chapter, we said, but these things also have their own magnetic fields. When we threw that in, got kind of complicated because it makes you think, oh, wait, this thing has its own magnetic field. That means that this magnetic field is going to cause a force on it. No. That'd be like you trying to pick yourself up. It'd be like you trying to put your hands on the bottom of your feet and you lift up and you pick yourself up into the air. It's impossible, right? And that's essentially what's going on here. So it has to be some outside magnetic field. Essentially the magnetic field from this bad boy, right, needs to be interacting. So it's this magnetic field, right? This is B2. This is I2. It's B2 that affects I1, and it's B1 that's going to affect I2. Okay, they can't individually. I just want to make sure we say that because we're going to talk about a lot of different things here all at once, and that's a very, very important thing. So we got two right-hand rules we got to go through here, right? We got two of them. We're going to draw that picture again. Don't worry, it'll come back. So we need just the right-hand rule for this, right? Which, you know, it's so different than the one before. So I'm just going to write underneath because it's going to work the same way, right? Where we said, like, in this case, L is going to be the direction of current, which is always like, you know, the direction that the arrow is pointing. I think everyone knows that. I don't think that's a tricky thing. And that's always going to be the hand direction. B is always going to be the, like I said, I say palm direction, but remember your palm can't curl in the way, I mean, your fingers can't curl in the direction of your palm. So you say palm direction, but your fingers will also be curling in that direction. And then this will be your thumb direction, especially if you're, again, doing it appropriately, where your fingers, you know, are pointed in whatever, your fingers and your thumb are perpendicular the whole time. As you start this whole, as you go from 1 to 2 to 3, your thumb and your fingers need to just stay perpendicular no matter how you're orienting your hand to be. And if you do that, then your thumb will be in the direction of FB without a finger curl, but still, you know, curl, you know, I don't want to tell you to not curl your fingers, but I see it, and it's so hard to do over the internet because when I'm in front of you, I actually will grab your hand because sometimes it's hard. Like you twist your hand when you curl your fingers, and that's okay. And sometimes I have to be there to hold your hand for you to fit. Once you feel it, you're like, oh, I see what I have to do here. But over the internet, it's almost impossible. So that's why I'm like, I'm so hesitant to say the finger curl because I see that's where a lot of things get messed up. But if you're following what we're saying, your thumb should already be in the direction if everything stays perpendicular. Okay. So this is is everyone cool? Do we have to go? I mean, it's just like, it's following the same directions, as this, right? It's just, you know, our essentially V is I here. That's the only difference. Okay, V is now the direction of current, which is still saying the same thing. Okay, and then the other magnetic field that we have, right-hand rule. So this is the right-hand rule for mag force on a wire. That's what I want to say. On a wire with current. Okay, so that's what that right-hand rule was that we just, like, it has a specific name. It's the right-hand rule for mag force on a wire with current. Okay, and then the other right-hand rule is for mag field, right? So this is going to be for mag field for a wire with current. We should probably say straight wire, but the other one we're going to say solenoid. So I mean, we separate them in that way. But you know, if you want to be really specific here, you can say mag field for straight wire with current, because that's actually even more specific and actually what this is. So very straightforward. All we do, right? If we know the direction of current, right? We put our thumb in the direction of current. which will always be in the direction of the arrow. And then the way, now also, please make sure you're using your right hand, okay? Please. The reason why I said this, because I almost just used my left. Okay, so put your thumb in the direction of the wire, and then literally the way your fingers would naturally curl around this wire if you wanted to pick it up is what you want to do. And as you would curl your fingers around this wire, that's literally the direction of the mag field. Remember, the magnetic fields are circular. Okay, they're always going to be circular. So you when you curl your fingers around this wire, you kind of want to like keep it kind of hollow, because you have a three-dimensional picture with your hand that's telling you something. Like yeah, it seems like a lot of times we're saying, oh, what's the magnetic field on the left and the right, right? But that's not always the case. What if I said, what's the magnetic field in the back of the wire? Who can tell me? What's the direction of it in the behind the wire? The same magnetic field, just what's the direction of it in the back of it?
Do you mean like the dots and X's, or?
No. So this is the left and right. So this would be, this is the right. This is the left. But what would it be like back here, in literally in back of it? Because this has a 360 direction, right? So what would it be in the back? What direction would the magnetic field be in the back? We know it's in on the right, out on the left. But what about in back? What direction would it be?
Would it be out on the left, in on the right?
So actually, I like what you're saying, and I think you're thinking about it at a higher level than you need to, my friend. You're saying good things. I kind of actually see what you're saying there. But in the back, it would, at one particular point, right, it's either going to be to the left or to the right, because the way this is moving, like essentially, if I were to just have the wire here, we know that like the magnetic field's going to be that direction in front, that direction on the side, that direction.
Oh, okay, I see what you're saying.
And that direction. I mean, these are 4 directions of the 360, right? But Dr. Newman's never going to ask you what's going on over, in between there. That's very complicated. We don't do that in this class. But these 4 directions are very much possible. So when we say direction, a lot of students, we think like just left or right, but you shouldn't. Like, keep in mind, like there's a 360 direction here. And so when you do the right hand, remember the point I'm trying to make is that when you do the right hand rule, you have this 3-dimensional picture in your hand that's telling you something. So as you curl your fingers around this wire, you're actually getting all those directions, because your fingers have to go. So let's do the right hand rule now. So our thumb needs to be pointed in the direction of this wire. So your thumb should be pointed up, right? And then as we go to grab onto this wire, right, we're going to have to do what? I mean, I know I would first put my hand in, orientation wise, I would put my fingers into the screen first, right? Because I need to pick it up. So my fingers need to go behind it, right? So I would go in on the right, and that's actually the direction of the magnetic field on the right, right? And then if I'm, again, trying to pick this thing up, my fingers would have to curl underneath. And in order for that to do that, I'd have to point my fingers in this direction. And every way that we point our fingers is a magnetic field direction here, right? Even as you curl them, there's 360-degree direction of this magnetic field. Here we're talking about only 4 of them, but in the back it's to the left. And then as I'm continuing to pick up this wire, I would have to then curl the tips of my fingers towards me, right? Where essentially now I'm kind of looking at my palm, where my fingers are facing me. My thumb is still pointed up, right? And do you see that 3-dimensional picture you kind of have? Like, well, your finger, you're looking at your palm, but it should be kind of curved, right? Where your wrist is kind of pointed at you, your fingers are kind of pointed at you, and then your palm kind of like curves away from you. And you should be seeing this because we use this picture later on to do other things, right? We have to understand this three-dimensionality when we're talking about generators and inductors, right? Because when we do inductors, you have to do this same right-hand rule, right? And sometimes you have to see the back or the front or something like this, right? So you've got to make sure, I'm just trying to make sure you all understand that when you make this curl direction around here, that we're not, there's more directions than just on the left and the right of this thing. Or if we're looking at this thing moving to the left or right, you might just be looking at like the top or the bottom, right? But there's more directions here, right? This wire, like in back, is moving up, and in front it's moving down, right? That's all. Those are also directions of the magnetic field. So just make sure you understand that. I just want to make sure you, because that's what this right-hand rule is trying to do for you. I mean, yeah, it gets you the direction of the magnetic field, but it literally gets you all 360 degree or all 163 directions of the magnetic field, I guess is the best way to say that. But am I making sense? Okay. So we need to put these two together, right? Like we'll individually do them, but then we're gonna have to, bring them together here. I hope if it posts, I almost already forgot to record it, but if it posts, it'll be on Canvas. Like I'll send out an email. So what is, if I have just a wire in a magnetic field, let's say the wire is moving to the left. Now this isn't the magnetic field for the wire. This is the magnetic field that the wire is sitting in. Okay. What direction is FB gonna be here? So put your finger, you're doing the top right-hand rule right now for mag force, right? So your finger should be pointed in the direction of the arrow with your thumb perpendicular. If your fingers are pointed there, I'm assuming your thumb is probably down. And then what do we need to do though? We need to flip our palm towards us, right? If your thumb's down, your fingers are to the left, your palm's towards the screen, but that's not the correct direction, right? Because here B's pointed out. So you want to make sure that you now flip your palm towards you. And when you do that, now your thumb is pointed up. Okay, with your palm facing you. And then if you want to curl, you can go ahead and curl, but like we said, this is already your force direction. You know your force direction. So yes, FB is going to be up. Everyone cool with that? All right. So, I mean, does anyone need to practice that more? There's not much more. I mean, we're going to practice it some more with other things, but individually, does anyone need to practice that more just by itself?
I just want to clarify, just like looking back at the equation you have at the top of the screen. Just finding the magnetic field is like how our fingers are curled, and that force of magnetic field is using like that other right-hand rule where we just dictated how it's going up, right?
So this equation, like this right-hand rule doesn't have an equation with it. I don't know if that's what you were referring to. I want to make sure I was kind of picking up on that. So I want to make sure that that's clear. You might not have been saying that. So, but let's see here. Yeah, I think the answer is yes. I don't know if I'm understanding your question correctly, but yeah, this is the right-hand rule for mag force. That's what you're asking, right?
Yeah. I just wanted to clarify the like, for example, B like magnetic field, and F of B, like force of magnetic field, they're not the same direction. Like they're not.
No, well, they can't. Here's the
Well,
thing.
they can be, but
Yes,
like,
yeah.
okay.
Yeah. So well, let me say this. They never can be. They never can be in the same direction. But I guess I was referring more to current, and I kind of made a jump there. I see what you're asking. Just something popped into my head when you asked that. You're asking something very good. Yes. So just like before, let me answer your question. I know exactly what you're asking.
Okay.
So just like before, right? We were saying, like, because this is a cross product, we know all these things are going to be perpendicular. So that is also going to be true here, where we know that if there's a magnetic force there, then that means that all three of these things are going to be perpendicular to themselves. So that means that, like, L is perpendicular to B, which is both of those are going to be perpendicular to F. So, like in this case, L was in the X direction, B was in the Z direction. And so the only direction that FB could have been in was the Y. And we just had to do the right hand rule to figure out that it was up. So we can see that FB here is in the Y, right? So they're always going to be, just as long as there's a magnetic force there, they have to all be perpendicular. But if he gives you a question, my friend, where he's like, the current is, so like, let's say he says, the magnetic field's in, but the current is coming out at you. Is there a magnetic force on this wire? So there's a wire there. It's in the green. I can't draw the wire because it's pointed at us, but the current is coming at us, and this is the magnetic field. Is there a force on this wire there?
No.
Right. Because they're in the same direction, right? So when they're in the same direction, you can't have FB because they have to be everything in order for FB to be here. L and B or Q and B have to be perpendicular. Okay, or V. Does that make sense?
Yeah, that makes sense. Thank you.
Awesome. No, that was a great question.
And I don't know if you're gonna touch on this or if it's like kind of a different topic. So if it's gonna like mess up your plan of what you have, to go for the rest of the session, you can, ignore this. But like imagine if the magnetic field was not uniform, if we had like some X's and some dots, for example, are we ever gonna see something like that? Or
like in the same, so you're saying like here at the, like a magnetic field, like something like this?
Yeah.
No, but you could potentially see something like this. I don't think so, but potentially. And the reason why is because this would be a change, right? The minute that magnetic field changes, we get a change in flux, right? So
yeah.
Right. And so that's what this would be referring to, is some sort of change. Like if I had some like wire and I was pulling it through here, well, here the magnetic field's one direction, right? It might be constant, but the minute that the wire gets right there, there's going to be a change in flux, and there's going to be a current in that wire, and all kinds of stuff. But no, you'll never see anything like that.
Okay. Thank you.
Good question. Yep. Mm-hmm. And I don't even know if that won before, but it's about it's about changes in flux, like how he presents the change in flux, right? It could come in many different fashions, because change in flux is just like literally the change in magnetic field, and that change in magnetic field, we'll talk about that here in 2 seconds, but could literally come in a lot of different ways. All right, so now what about when we have two wires sitting next to each other, right? Well, we know they're going to affect each other, right? And they're going to affect each other based off of the magnetic fields that each one of them produce. So in order to figure out how these are going to affect each other, we have to first find each individual one's magnetic field and then apply the magnetic field that we find for one wire to the other in order to then get the magnetic force. Does that make sense? We're going to do all this. I'm just laying out the plan. Does that make sense? So anytime you see two wires sitting next to each other, your first job is to get the magnetic field direction for the wire. And not just magnetic field direction, but magnetic field direction closest in orientation. That's orientation. Closest in orientation to the, let's say, other wire of concern. Does that make sense how I'm saying that? Like, it's not just finding the like I could find the magnetic field behind this thing, but that ain't going to help me here, right? I need to find the magnetic field that's going to be interacting with this wire over here. So I need to not just find the magnetic field direction, but the one closest in orientation to the other wire that I'm trying to see is being affected by the one I'm currently finding the magnetic field for. Does that make sense what I'm saying?
Yes.
Then the next thing we're going to do after we find that magnetic field, so that's for the individual wires, then we're going to apply mag field to opposite wire. Hopefully that again, if this doesn't make sense, I'm kind of making these directions up on the fly, but we're going to walk through them all. So they'll definitely make sense once you see them all. Then you can make adjustments to these directions how you need. And then after that, then we'll be able to get FB using this equation on each individual wire. Okay. So it doesn't matter which one we start with, but let's just start with I1. So we need I1's magnetic field, and let's go ahead and you know, if we get one, we can get the other. We don't have to get all four, but let's definitely focus on the pair that's associated with like the orientation that we're looking for. So here, because this wire is sitting next to I2, I'm concerned with the magnetic field over, like that's the most important one for I1. And for I2, the most important direction for the magnetic field would be on that side. Does that make sense what I'm saying? Because this is the closest in orientation to this wire. This is going to be the closest in orientation to this wire. Does that make sense?
Yes.
Cool. So but like I say, you know, if we get this side, we can get this side. So we can get both. So what's the magnetic field on the left and right? Let's just do the right and left. Okay, in on the right, out on the left. Does everyone agree with that, or should I change it? Good. Awesome. Okay, and then for I2, left, what would be on the left and right here, or right and left, however? Good. Right, they're in the same direction, right? So nothing should change here. Good job. I should have done that in blue. Okay. So now, like I said, we're concerned with this, and right. Those are the two directions we're concerned with because they're closest in orientation to the opposite wire that they're interacting with, right? So it's up to you. All right. And I was talking to a few of you and you said that it kind of helps to do this, but I want to make sure you're seeing everything. So one good thing to do is to like literally write this direction. Oh, like, you know, just don't think about it, like write it over here, but make sure it's so, you know, we're writing these two on the left and right, but the one that's being applied, like draw it right on top of the, right. This is I2. I mean, sorry, B2. This is B2. I should have labeled these. B1. This is B2 right here, right? That's going to be the direction of B2 on B1. Does that make sense? So just draw it on there. Like don't try to visualize this. Put it on there. And then the same thing for I2. And we're at the second step, by the way. I forgot to say that. Now we're applying the mag fields to the opposite wire, right? So I wanted to apply B2 to I1. And now I want to apply B1's direction, which is the one closest in orientation, to I2, right? Which would be in. So again, and then label them up, right? That's B1. All right. So now we get force. Now we're on to step 3, which is now we can get the magnetic forces for both of these. Sometimes he might, right? He might just ask you for I2. Right? He's just like, what's the magnetic force on I2 from I1? But let's get them for both here, okay? So, and we're using this right-hand rule, the one at the very, very top, right? Magnetic force on a wire with current. So we want our hand pointed up. Okay, your fingers should be pointed for, we're going to do I1 first. So your hand should be pointed up. And again, it's up to you. You might already orient your palm right away, but I'm going to start from the basics. So I'm just going to point my hand up, and I want to make sure my thumb's perpendicular. Then the next step I know I have to do is I have to orient my palm in the direction of the applied magnetic field, not I1's magnetic field, but the applied one, which is B2. So here B2 is out of the board, right? So I want to face my palm towards me. And when I do that, essentially, right, your thumb flips direction. And now, like I said, if you want to curl your fingers at this point, go ahead, but your thumb, because we're doing this perpendicular thing, is already pointed in the right direction, which is saying that FB, right? So FB is this way. And what does that mean? What does that mean I2 is doing to I1?
Does that mean that it's attracting it?
Absolutely. Good job. Good job. Good job. All right, now for I2, what's going to be the direction of FB? So go through all the rules. I'm letting you do it on your own now, but we'll do it together. We're getting to the left. So a finger should be pointed up towards the top of the, I mean, that's how I'm starting, up towards the top of the screen, thumb to the left. And then I want to look at next, because I'm just looking at current direction right now. Next, I want to look at the applied magnetic field, which is B1, which is in. It's in over here. So my palm should be facing the screen, and then my thumb's already in the right direction, but if you want to give that finger curl, go ahead. Which, good job. That means that's direction of FB. So there's actually a concept here. Dr. Ngana, I don't know if he's asking you to memorize it or not, but he does want you to know these things, right? So when current's going, when two wires are next to each other and the current's going in the same direction, they attract each other. And if you're saying like, oh, how fun and cool. Yeah, you want to know something even cooler is the why, which is mind-blowing. It's because, look, what do we know about magnets that have opposite poles? Essentially, this is like a north and this is a south. Are they going to attract or are they going to repel? Yeah, see, that's what this is telling you. Right? They're just in opposite directions of the magnetic fields. They attract. Right? And if this wire, it doesn't matter which one, but if this wire was down, right, that means that the magnetic field is going to be out on this side, which means, look, now they're in the same direction, which means they should what? That's like two norths. Yeah, see, they're both pointed out at us, right? So before they were in the opposite direction, but now they're both pointed out, right, at us. The interacting magnetic fields. And so they're in the same direction. That's like bringing two north poles together. What are they going to do? There you go. And that's why. See, the why is even cooler, huh? They're literally turning into magnets, these things. Mind-blowing. Okay. So that's so the one other thing that we need to discuss to make sure that we understand here, right? Let's just look at a cleaner picture. Is the hold on, let me just do this fast and then see this time. Is the equations. Okay. I just want to give a little bit of what we had. Okay. So what are the equations here? Well, one of them, you know already, right? We know, you know the F equation that we're using here, right? You know, it's the F. Now we got to label it up. That's what's super important. That's where he tries to get you on the test. But we know that, like, you know, in terms of the equation, oops. That's the FB equation we're using. But we also have magnetic field here, right? we need an equation for that too. So what would that, does anyone know what equation, or there's a name, I guess I'm looking for a name. I mean, if you want to just tell me the equation, you can, but. Oh yeah, nice. Ampere's law, right? Ampere's law, it's the equivalent of Gauss's law, okay, for magnetic fields. Remember, Gauss's law got us electric fields at a certain distance away from the source of the electric field, right? So if I had, you know, a charged plate or something like this, and I needed to know the electric field over here, right? I could use, or let's say this is a wire. If it was a plate, this picture would be kind of messy. I would use Gauss's law, draw a Gaussian surface, blah, blah, blah. Well, you don't need to worry about Gaussian surfaces with Ampere's law, because we know these things, right? They're better. They just circle and in the same place, right? From the same source. It's just this 360 degree, right? So if I got to find somewhere out here, I don't need Gauss's law. I know it's still just going to be this certain radius from the center of that particular point, right? And so that is what Ampere's law is doing for you. And so the equation, so there's a few, right? And I'm pretty sure, but please check that Dr. Dungana labels them for you. So I believe he has like, because he's not showing you how to derive this. There's actually, just like we derive Gauss's law. Remember, we used flux. For Gauss's law. Well, believe it or not, Ampere's law has the same situation. There's two flux equations that go along with it, and you can derive it, blah, 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 blah. But I don't think he does that to you. I think he's directly giving you these equations. But please make sure, because you're gonna need it. Okay. So that's the magnetic, and he also labels them for you. So that's the magnetic field for a straight wire, right? So that's what we have to use. Like essentially he'd be asking you, you know, what's B2 and B1, right? We'd want to know B2. He'd be asking you, what's the strength of B2 at I1, right? We know this is I1. We know this is I2. And essentially he would ask you, if he were to ask you for an equation here, he would be asking you, what is the magnetic field of B2 at I1? What is the magnetic field at B1 for I2? Now, maybe not for the number, right? He doesn't have you do much calculations on the test, but he would definitely ask you for the equation labeled properly. Okay, so let's just start with B2. It doesn't matter which one we start with here. So what is going to be the value of a B2 here? Good. Right. So that's really our only variable. I should have said that's my fault. So we see in B the equation for it. It's really just right. We know R is going to be the distance right between them. So it's really just based off that I. So good. We are trying to find out what current we should use. Well, what's the source of B2? It's I2, right? So it's that simple. Nothing tricky, right? And again, R's that you're trying to find. Remember, this R is going to be the point where you're trying to find the value of the mag field. Okay. Darn it. It's messy. Okay, so that's what R is like. That's the location. They're like, what's the magnetic field here? Well, that's R. That would be that spot. So I is really dictating the B. The current's making the B. So since I2 is making B2, everyone cool there? Okay, so then what is going to be B1 then? I mean, it's pretty obvious, but. Yep, just use I1. Yeah, that's what I was actually, I guess I should have asked that better. But yes, that's what I'm looking for is yes. Yep, good job. All right, and then what would the forces be now? So it doesn't matter. Let's just do, what would the force be over here? Like the value of it. He would, he'd be asking you, what's the value of FB, from I2 onto I1. Might not ask for an actual number, but definitely an equation. Okay, so yep, we need the one at the top. So let's start there. Let's write that. I like that idea of writing that out first, and then we can label it up. Ah, there we go. Yeah, so what should be the I? First of all, actually, let's get rid of this thing. It's always a good thing. What is this thing? It's easy to get rid of. We know these things are perpendicular, so that's going to be 1, right? I'm doing this so you watch me use this equation every time. I don't just use this, okay? We don't do that. Always start with this, get rid of it every time, okay? There we go. All right, great job. And then what's going to be or did you already tell me? I1. Is that what you were? Yes, I got. Yeah, that's yes. I was told, and that is correct because that is where we're trying to find the force. We're trying to find the force on I1, right? So this force is going to be felt on I1, so that needs to be the current in there, right? I2 is the source of magnetic field, but I1's the one feeling the force. Okay, and then the magnetic field. So use the same thinking that I was trying to hint you there a little bit. That's a great question. So we're finding the FB, like we could label this, 2 onto 1. So, we can write it there. But this is the force we're talking about right here. No matter how we label it, I don't think it makes it any more clear. But maybe if I, actually point to it, that probably shows. So we're trying to find this force, right? This force is being felt on I1, right? I1's the one feeling that particular force we're trying to find, right? So that's why we're using I1 here for the FB, right? But then why is I1 feeling the FB? Because of this magnetic field that's coming from where? Do you see how I'm saying, I'm explaining that, Juliana? Or I want to make sure that makes sense what I just said.
Could you say that again? Sorry.
Yeah. So right now we're looking for the force onto I1, right? Oh no, absolutely. I would. This is complicated stuff. So we're looking for this force, right? This force, it's there because of the magnetic field from I2, but I2 isn't the one feeling this force right now. We're talking about the force on I1. So I1 is going to be the one that's going to be feeling this force. So that's why we're using I1 as the current in the FB. But then again, just to reiterate what I just said, is that because this force is only there because of the magnetic field from I2, therefore, we need to make sure that this is going to be B2 in here because this force is being generated by the interaction of I1 and B2. Does that make sense? Because B2 is the thing that's affecting it, right? And so this FB is a result of the current that we're specifically talking about and the FB that's interacting with it. Does that make sense?
Gotcha. Yeah, I got you. Thank you.
Absolutely. And that would have been true also with the thing that we were talking about over here. It's just better to kill 2 birds with 1 stone there. But where did I have it? So you can do the same thing here. It's just like if you just have a wire just sitting in a magnetic field, you can still find the force on it, but now you're not trying, you're not concerned where this magnetic field is. We're just calling it B. But when you have two wires sitting next to each other, right, you have to kind of like consider the situation. But I think everyone's understanding. I'm digressing too much here. Okay, great. So what would be the FB on this side now? This force right here. So what would the force that the I2 would feel from the magnetic field from I1? How would I write that equation? Good. We know this goes away. I just have a bad habit of doing that. So let me try it here. I saw the answer. So I2B1 is what I'm getting in the chat. Is that true here?
Yes.
Perfect. Good job. Okay. And then you would use this equation, right? The point of that first equation that we got would be to use, right? I mean, you'd probably have a number here by now, but that could go in there too, potentially. I mean, I don't know, but just keep that in mind. That's how those two equations interact with each other. That's why we got an equation for B2, because we needed it for the FB. Okay. So I think that's let me ask this. Do you need more practice on two wires now we don't have to go through all the math, but do you want to see a few more examples in terms of wires, and then just using the right hand rule and like getting the forces between, like maybe a hoop and a wire and stuff like that? Okay. Because I mean, he can ask you a ton of stuff. Actually, one question he asks here, believe it or not, still associated with this question, is he actually I've totally seen him ask. I think he asked this in class. Absolutely. What would happen if I said, let's start with this, but this, we're going to do more. What would happen if I sent a positive, charge between these two wires? Would it be affected? Would it also feel a force? Because we know that there's these two forces here. So there's these two forces. The wires are applying forces to each other, right? If we were to like send a particle between these two wires, would it feel a force too?
I think it would be like having forces act on it, but no net force. If that makes sense.
So no net force would be like there's two interacting forces.
Okay.
Like if we're saying that there are forces present, but there's no net force, that means that there must be a balance going on somewhere. So we need like two forces for that balance to occur. But if there's just like one force there and nothing to balance out.
So would it not be the two forces from those two wires that would be like canceling each other out, giving no net force?
Okay, I see how that could be definitely seen. That's not, I'll show you here in a second why we don't want to do that, but that's not quite how we're looking at it. All we need to do, so some of the things that came through the chat are brilliant. So what we need to do is remember, we just go back to this equation. Is what we need to do. That's the first thing you need to do. And you need to say, okay, V got that direction, but what's the direction of B here? That's really your concern, is what, if we want to know if there's a force applied to this particle, we just can't look at the question. We have to go through the right hand rule. And so what is the direction of B? Well, we see that B2 is in, and that's going to be true right here where the particle is too, right? B2 is in, and B1 is out. So they have opposite directions, right? And they're going to have the same. This didn't become relevant till now, but I should have said, like, that strength will be the same if it's the same amount of current running through both. So let's say that the same amount of current is running through both. So those magnetic fields will be the same, but in opposite directions. So the magnetic fields are canceling themselves out, which means B is going to be equal to 0. There in the center. There's no magnetic field in the center, right? Now there's a net magnetic field here, and there's a net magnetic field here, because remember, at I1, there is no B1. B1, and that's what Ampere's law is trying to tell you, is that the magnetic field isn't there until you're some distance away from the wire. If you're on the wire, there's no R would be 0 in that case. So there's no magnetic field on. So B1 doesn't exist until you get some distance from I1, right? So B1, there's a net magnetic field on I1 and I2 because they can't cancel each other out because of that reason. But anywhere here in the center, they're going to have an opposite but equal magnitude situation, which means, if we sum them, which we can say B1 plus B2, but since they're in opposite directions, it would be this, they would be equal to 0. And so this would be 0 in this equation, which means there wouldn't be any FB on it. Does that make sense? Like, that's how you want to think. Cool. Now, here's where the proof of the pudding is, right? Because when we look at these two things interact, yeah, this is same for protons, or it doesn't matter the charge. Like, if we send it through that, like it would be the same. That's a great question. We would use the same, like the only thing that would change, like, this could be positive or negative. Okay, this is still 0, and if that's 0, right, then it's still going to be. That was a great question. And then here, right, so believe it or not, when these things, and I suggest, later on after the review, go home and check it. You can always send things that you do on your own to me. I'll check them for you. So will Dr. Dungana. They don't have to be our stuff, but if we give you something, you can always do it on your own and send it to us. We'll always check it for you. But what happens in this situation, because of the way that the magnetic fields are working out here, right? It's I'm just going to draw the important ones. Moved on to the right. So they're both in terms of orientation to themselves, right? So we see that, like, anywhere in here, right? This is B1, this is B2. Okay, these are the Fs. You can go through everything and check those later. But what we would see here is that, see, B and B are in the same direction here. So in this case, B1 would be plus B2. So we have these forces that are pointed in two opposite directions, but that has nothing to do with what the particle's about to do when we send it through here. So now what's going to happen if I send a particle through here? This is why he's asking you this question. Use the same thing. Remember, you got to use this. So here, they're in the same direction, and they have the same magnitude. So essentially, this is 2B, right? So what does that mean about this then? And now you're going to have to do the whole right-hand rule, not just the equation. So you're going to have to tell me the direction that it's going to be affected in. Oh, I'm sorry. I used the wrong one. It should be. I apologize. So fingers should point towards the top of the screen, right? Thumb pointed to the left. Magnetic field is pointed out of this in the center. Anywhere in the magnetic field is pointed out of this. And so our palm, you face your palm towards you. Now your thumb should be pointed to the left and your fingers pointing to the top of the screen. If you want to curl them, go ahead. But we can see just from that FB is going to be
I'm sorry. Correct me if I'm wrong. Is the thumb pointing to the left or the right?
When you're all done, it's pointed to the right.
Oh,
right?
okay.
our fingers are going to be pointing. So this is the direction. This is the direction of FB here. So to start this all off, let me go ahead and draw it. Like I said, I almost have to draw it for you every time. It's important. Just I want to make sure you understand. So I'm starting with my hands like this, with my palm facing the screen. So my thumb's going to be in that direction in terms of my fingers. And then what's going to happen, and that's V, right? That's my fingers just in orientation to V. And now I see B's pointed out at me. So I got to flip my palm towards me. Now my palm's facing the screen, but now I want to flip my palm towards me. When I do that, now my thumb, right, essentially flips directions. Now my palm's facing them. My fingers are still faced up. And if you want to, now you can give a finger curl, but we see that this is going to be the FB, right? Once you curl your fingers. Everyone cool with that? Cool.
Yes, and if this was an electron, then it would be flipped, right?
Yes.
Okay.
Yes. So essentially, a proton would move this way, and an electron would move that way. Yep. Absolutely. Great question. They would separate. This would cause them to deploy. So it'd be nothing. Actually, this is no different than what? This, right? Sending the blood through the magnet, right? There's a constant magnetic field here, right? So the charges we saw separated in different directions. That's what's happening here. Okay. Cool. Any questions about this? I'm trying to look at everything here that we've done and make sure we covered the important things so far. I mean, there's always stuff to talk about. Well, at least up to this point is what I should say. But does anyone have any questions? Kind of rest your brain a little bit. Because if I just keep talking, that, not that it hasn't already happened, but you'll eventually say, oh, we wanted to practice a little bit more. That was the next thing to do. Okay, let's practice a little bit more here. And then we can move on to induction, okay? So just a couple more, right? And like I said, we're not going to go through any of the equations or anything, okay? Let's essentially just to remind you, you're going to be using these directions here, which is you're going to be finding the magnetic field direction closest in orientation to the wire of concern. We'll apply that magnetic field to that wire, and then we'll get the FB on that wire, okay? I'm not going to worry too much about these. That's supposed to be perfect, okay? And then I don't know why it's so hard to randomly do things, but it's okay. My brain just doesn't want to like randomly pick. I don't know why that was so difficult. All right, so let's look at the magnetic force on this wire up here, because these are typical. That's typically what it is. But we could look at this thing on this thing too. Like it doesn't, but it would work all the same. Okay, so how do I find the FB on this wire? Or do you want to just tell? Let me just add. We'll do it together. How about you all do it on your own real quick? Get an answer in your head. Okay, and if you want to give it to me, go ahead. And then we're going to do it together to check it though. So if you don't want to give it to me, you don't have to, but get an answer in your head. Okay, do it on your own. Say, I think that, remember, you're trying to find the FB direction on this. What is the FB from this thing, right? This thing's going to be affecting that wire and essentially causing a magnetic force on it. So I just want the direction of this. Everyone good? And take your time. I'll give you a few more seconds here. And you're using both right-hand rules as well. Keep that in mind. Okay, so let's do this. Like I said, you don't have to give me an answer. But if you want to, go ahead. I don't mind. I'm not too sure. We're gonna do it together. We'll find out together. I just don't know. No, I trust you. Actually, I think you're right. I just don't know. Don't be sad. You know, I think the world of you. Okay. All right. So let's do this. The first thing we need to do is we need to find the magnetic field on this wire. There's too many arrows going on. We need B up here, right? From this, let's call it B. I don't know, coil or something. Okay, so we need to find the B from the coil up here on that wire. So what is the direction of B on the wire? The B from the coil, on the direction of B from the coil. So we can do the right-hand rule where we put our thumb in the direction of current. So if we start with this wire, right? And we put our finger in the direction of current and kind of curl our fingers around this wire, we can see that the magnetic field is going in on top. Does everyone agree with that? And out on the bottom. Cool. And then because there's current all the way around, now he talked about something here, or maybe you can tell, maybe some of you know, and then we don't need to go through, we can just talk about it in terms of concept. But are we concerned with these two wires over here? Again, he's talked about this, so I might not need to say anything. You might be well versed in this. And why not? What's the simple answer there? Yeah, sine theta. So these magnetic fields are going like this, right? A lot of good answers there. Are these ever gonna like go up here? So that's the most, like, you should have that picture in your head. Like, I mean, yeah, everything you all said was beautiful because I love math and you were talking my language there. But when you think about this thing, these things are just certain. So there's no, like, I don't care how far out we go, it's never going to go up here. So we can just look that way. Like the B's from those two, they just don't interact with the wire on top, right? So that's why we can ignore it. And then for the bottom one, right, same situation. Thumb in the direction of current. Then we wrap our fingers around this. So, right, well, you'd put your fingers in on the bottom and then out on top. So there's a trick here. Now, remember, you can't use this all the time, but it's the second right-hand rule, actually, that for magnetic fields that you can use here. So the second right-hand rule for coils, right, is, and this is to find the mag field for coil, which is also, it's the right hand rule to use, like if you need, because let me say this, because they're interchangeable. When I write those, they're actually interchangeable, because over here I said like the mag field for a wire with current, but keep in mind, if you know the direction of mag field, you can also get the direction of current for this right hand rule. If that's not making sense, let me show you why. So like I said, this right hand rule, the way it's written, it's saying how to get the magnetic field for a wire with current. So we said, okay, we'll put our thumb in the direction of current and then curl around. So we know the magnetic field does this for this. But what if you didn't know the direction of current? What if I just told you I have a wire and the magnetic field is this way? Which direction is current going to be? Just use this right hand rule over here still. This time you're going to curl your direction in the magnetic field and you're going to look at what? Yeah, good job. You're going to look at the direction of your thumb, right? So these are interchangeable. Keep that in mind, okay? They help you get the magnetic field for the current, or they help you get the current for the magnetic field, right? If you know the magnetic field, you can curl your fingers literally in the direction of the magnetic field, and your thumb should be left extended as you curl your fingers. And when you do that, your thumb ends up pointing down. That's the direction of current here based off that magnetic field. Does that make sense? So it's the same thing over here with this right hand rule. Right now I'm writing it as mag field for a coil with current, but this could also be getting the current for the mag field, right, for a coil. you see what I'm saying? I don't think I said that right, but I think you all are picking up on what I'm saying. I just can't say it correctly. Okay. So the way this one works is you curl fingers in direction of current, okay? And you do that with thumb extended out. And then your thumb direction as you curl your fingers is going to be the magnetic field inside the coil. Now this is only true if right here the current we see is moving all in the same direction. But and trust me, I've seen these things, but the current over here is moving up, and they're going, if for some reason it doesn't make sense, then you can't use this right hand rule. This is only true when the current's making a full loop. And so you curl your fingers in the direction of the current, and then the thumb is going to be the direction to be inside the coil. But if you know the direction of the magnetic field inside the coil, then you also know the direction of the magnetic field outside the coil, because it's going to be the opposite of what it is on the inside. Does that make sense what I'm saying? If not, you'll see it about to happen. So here, right? Let's check ourselves. Let's not have these there, and let's see if we get the same answer though. So now let's use the right hand rule. Remember, this right hand rule is going to get us the direction inside, but then we'll also know outside. So if I curl my fingers in the direction of current here and leave my thumb extended, which way does your thumb end up pointing? Curl your fingers in the direction of current for this coil, which is around this way. So just follow that around. Curl your fingers just like this. And which way? I got one answer, but I want a few more to make sure we're correct. Is Juliana right? Juliana's saying out of screen. So again, just curl your fingers in the same direction. So they should be essentially curl your fingers, in this case, counterclockwise, right? And your thumb's pointed out. So yeah, so that's the magnetic field inside this coil. Remember, you can use this for any coil, okay? So when we talk about coils, you'll already have this in your back pocket. For like induct, right? That's where induction is with the coils and stuff, right? But this is how we use the same idea. And so the outside here is going to be in. Because of that. Cool. So that's the fast way to do. I mean, they're both fast, but you should know both ways. Okay, you should know how to do it both ways. So that's getting the magnetic field direction using that. But remember, you could also, oops, not that one. You can also do it, using this one too. I mean, essentially. So, all right. Cool. Okay. So what is the magnetic field direction and orientation for this wire up here due to that coil? It should have two directions, just to hint you. Right, I got rid of all of the magnetic fields except the ones we're concerned with, right? Those should be the only two we're concerned with. And why is that?
Because they're parallel with the other wire.
Yeah, in terms of their orientation, that I love the way that's exactly. Yep. Just like, right, it's all about orientation. So this is in terms of this wire right here, this is the magnetic field it produces that's closest to this wire, but also, right, they're parallel. But really, I would, it's more about what I just said with, looking at the orientation, because this one also has an out, but we don't want to use this magnetic field down here because it's furthest away from the wire, right? This in terms of the magnetic field for that current on the bottom, that's the one that's closest in orientation to the wire that we're trying to find the force for. So we'll call that, and it's good to label these, right? This would be I1, so that would be B1. So this would be I2, so that would be B2. So for I1, right, we know B1 is going to be in this direction, right? So that's B1. All right, what about B2? It's going to be, we can clearly see, going to be in the opposite direction, right? So that's B2. So how do we know which one to use here? Good job. Right, B2's, I mean, you can see it. B2's closer to I1, so it's going to be much stronger than B1. So even though they're going to interact, and yes, we should, just like the last question we just did, right? You can like net these; they're in opposite direction, right? And we know B2's larger, so let's put that first. And so when you do this math, right, there's going to be some number left over, but this is going to be essentially the value of what's left over of B2 after, B1 kind of cancels out a little bit of the B2 that it can, right? So B2 is going to be left over simply because it's the strongest. Good job. So those are the two that we need, but then that's going to end up being like B net. That's what we should call it, right? And that's what this. So good. And so now which direction is the force then? So our hand should go to the right. Palm should be facing towards the screen. Good job.
So like theoretically, if we ever get one of these questions, could we just use the part of like that coil, the part of it that's closest to the wire of concern and just ignore the other bottom one? Like I know they both play in, but since one's going to be stronger than the other and like
Yes.
overwhelm it.
Let me say this, my friend. Just as long as the current is the same all the way through here. For some, Dr. Uganda wouldn't do this. I just got to say this, okay? Probably more for your understanding than actually you getting a question with that being in it. But if for some reason this I1, its strength makes up for the difference in this, like, this is weaker, right? And this I1 down here is actually stronger, and it makes up for the difference. They could actually be the same. Do you see what I'm saying?
Yeah, I get you.
And so that comes in with the the equation for you can find the current. It's very easy.
Okay, thank you.
Yep, absolutely. Great question. Like you can rearrange this thing to find current. A lot of things, right? But okay, like if you know B, but all right. Did you want to do any more practice here? That was the answer you got, right? A few of you gave me an answer earlier. Now I can't seem to find it, but hopefully that was the one. I know I can't find your answers. Gosh darn it. But hopefully that's what you got. There was two of you that gave me an answer. Okay, let's move forward. We need to review, but I'm proud of all of you. Great job. Do you want to do any more of these? Okay, and also please, I mean, most of you have been coming to SI, but please, when you look at his worksheets, they are so straightforward. He's not doing any of this stuff on his worksheets, okay? Nothing. They're so straight. They're all based off everything we've talked about, you can do his worksheets already for these next two sections because they're only about using the right-hand rule and getting FB. All this other stuff, right? Well, in terms of this stuff and then the induction stuff, you need to know, which is what we're going to talk about. Okay. Oh yeah, it's real for this section. It's so easy to, because he just throws a wire in a magnetic field. He just wants you to get F and B, right? He's not putting any wires next to each other. It's just so straightforward. Yeah. So don't make more of it. But please, if you didn't come to SI and you have those done, you can send me the key. Or also keep in mind, we can work on them tomorrow. Okay. I just want to get through as much of this material as we can in terms of talking concept and stuff like that. But if you want to work through worksheets tomorrow, we can work through every single one of them. Okay. Absolutely. Okay. So let's do this thing. Induction, because this is where it's at. All right. So first let's walk through the process. All right. And then everything else will be actually pretty clear. Like, and just like before, for the first test, I kind of gave you a chart that'll help you flow through things. This chart will help you do it. Okay. So I would suggest to use this chart or have it in your head, because it'll answer quite a lot of his questions for you. Okay. In terms of induction, what's going to happen, what's going on. So induction, how does it work? Well, the first thing we have to have present is some magnetic field, or what we call B original. Okay. And then with that magnetic field's present and we add a conductor, and it's very important that it's a conductor, because that has the loose electrons to allow the charges to separate and induce the electric field that we need. That in itself, it's the conductor itself that designates the area. Now, it might be the actual, like if it's a plate, right? It might be like the area of the conductor itself, right? But like he gave you this question with the sliding bar, right? Well, this bar, right, that can slide back and forth, when we add this bar here, this now, it designates the area, right? And this thing slides, remember he told you this thing slides back and forth. So the area can get larger and smaller based off of how this conductor is, like here, the area is this, right? But if this thing were to, because it can move back and forth, if this thing happened to slide over this way, right? Well, now the area becomes this, right? So this is area, right? So there's a change in area simply because the conductor moved and reestablished like a new area for this system, right? So my point is the conductor establishes the area. You need to sit there and say, okay, how did this conductor establish the area? Did it do it like this way, in a very complicated way, which I think this is the only complicated way you see? Or is it the conductor itself setting up the area, which is more than likely what you're going to see. Definitely what he does on his worksheets, which is like he has a magnetic field, right? This would be the original. And then he let me need this space. And then he throws a hoop in here. And then, that hoop, the area of the hoop, that's the conductor also. It's establishing our flux. Okay. So when we have a B original and we add a conductor, the conductor establishes the flux, not a change in flux, just the flux. Okay. And again, flux is just how many field lines are present in a particular area. And Levi, you asked me a question about, you asked me one time or something about flux not being real. I mean, it's not, I thought about that a little more after you asked, like, it's not real in the sense that, like, we establish flux. Like, it's not something that's there until we say this area. So, yeah, you could definitely hear people say like flux isn't a real thing. Well, no, it's not. It's not there until like a physicist or an engineer comes along, right, or someone, and then like establishes some sort of area. Like, we don't even have to establish it in terms of a conductor. We could just say like this area. Well, now that's flux because we said that there's field lines in this particular area. There doesn't have to actually be an object there for flux to be there. We just establish it mathematically. So that might have been what you were reading, Levi. But flux is a thing, right? And flux is how many field lines are in a certain area. So the conductors establish the area, and because the conductors are establishing the area, they establish the flux. Yeah, so flux is not specific on any type of field. You could also gravitational flux. That's a very important thing in physics. There's a flux is just field lines. What we say in physics is just field lines in a particular area. Electric field, magnetic field, gravitational field, all these different things. Yep, just that's flux comes from mathematics and not from physics actually. So once we have that flux, now you can get a flux, but when you start to have some sort of change in magnetic field, change in the to write delta area, or change in the theta, which is, you know, something just that's sitting in one place, but you know, if I were to rotate this wire in that one place, now there's a change in, you know, theta, but you can still look at the change in area kind of correlates to the change in theta, which is kind of nice. But we'll talk about that here in a second. But you have to have a change in one of these three things, right? Because we know that flux is equal, it's a dot product. And it's based on, I guess that's less important, but more important to know that flux is based off of magnetic field, area, and the angle between the two, right? So if I need a change in flux, then that means I need a change. Wait a minute, I need to move that. That means like any of these things, I don't want to get complicated here and write a ton of equations, but right, like change in flux, right? We can have, you know, or a combination. It might not just be, right, like here I'm saying just a change in B, but no change in A or theta. Or here, just a change in area and no change in B or theta. But it could be a change in both. I can have a change in area and change in B, trust me. Other professors that teach the algebra based, like I've seen those questions, you guys have no idea how nice Dr. is. He's so nice. He loves you all so much. He really does care about you. He doesn't want this physics to be a burden on your transcripts. If you were to talk to him, that's the honest truth. Okay, so so we change in theta, change in area, change in magnetic field, right? A change in any of those or a combination of them, that then gives us a change in flux, right? And when we have a change in flux for a certain amount of time, right? Because the flux, if it's changing, it's got to be changing at a certain rate, right? All changes occur at a certain rate. So that's all that is when we put it over time. We're just saying, okay, the flux is changing, but at what rate? Right? When we have some rate of change in flux is what we say, then that's where we get an induced electric field. So again, when we got into because we're not going to talk about the electromagnetic field chapter so much today because it was a small chapter. He just wants you to know one little thing in there. But that chapter is more for application for you to see where this naturally happens in nature. But look at this, is like, you know, we told you in that chapter that electric fields automatically induce magnetic fields. Magnetic fields automatically induce electric fields. They don't need a charge around to do it, right? They're going to just naturally induce themselves. And so what I'm showing you right here, and what we showed you in class before, is like, you know, where this happens in terms of you physically being able to see it. But here, like with a photon or something, like you can't physically see this change, but it is also something that's still occurring. Just like we see this magnetic field's inducing this electric field. And then what do we see after that? This electric field induces a magnetic field. Well, yeah, if that can happen, then why can't this electric field and magnetic field induce themselves all on their own? Like, that's really the only change there. So that's all we're trying to show you with that chapter. But what's important is induction in this stuff here. Okay, so once we have that change in flux and we get that E induced, I mean, you can't stop this. I think I've told a lot of you, this is just like entropy. Okay, you can't stop this process. The minute this happens, you can't stop it. Sometimes it's a bad thing. Okay, sometimes it's a good thing. All right, but once you have that change in flux, you get an electric field that's induced, which then induces a current, which then induces a new magnetic field. And remember, that new magnetic field is just the magnetic field that's, you know, associated with that current. Okay, so this is the process. need to be original. This would be considered be original, okay? Then we need to add a conductor. Then we need some sort of change in flux. Here we can make the we could make the wire smaller, like go from big to small, big to small, big to small. That is going to be a change in flux just due to area. We can sit here and like that magnetic field might be hooked up to some sort of dial that we can turn up and turn down, so that area of the wire might not change. But if we're cranking up the magnitude of magnetic field or turning it down really far, that's going to also be enough for a change in flux. And then also just spinning this thing, right, where what happens, and this is also how the generators work, right? As this hoop starts to spin, right, it's going to spin, it's going to spin this way. Let's just say it could spin anyway. Then less and less of it's going to start to interact with the magnetic field, right? There's going to be a point where the hoop is going to be essentially sitting like, we wouldn't even be able to see the hoop. It'd be like perpendicular essentially. And here we see that none of the magnetic field is going through the hoop, right? The hoop is essentially in the Z direction as well, right? Along with the magnetic field. So there's no flux here. But as the hoop gets to that position, and then as the hoop moves away from that position, back to this, right? There's a constant change in flux, right? Because just the amount of magnetic field lines that are going to be inside that hoop are going to be changing. As it twists, it might just go down to 2, right? And then there's not going to be any. And then as it twists back, right, there's going to be 2, and then eventually all 4 again, right? As more and more of the area starts to re-interact with that magnetic field. And so this right here is Faraday's law. I'll just write it off here to the side. I'm writing that backwards. So E induced is equal to a change in flux over delta T, where yes, any one of these equations can pop into here. Okay, and then Lenz's law tells us this thing that allows us to use this as a concept to answer questions, right? It's great to know that this process occurs, but then Lenz's law gives us something where we're able to, look at particular systems and actually conceptually say, oh, this is going to happen, or this is going to happen. There's going to be a current generated. It's going to be in this direction. Why? Because flux is changing or increasing or decreasing in a particular way, right? And that's all Lenz's law is trying to do for you. Okay, so for Lenz's law, who knows it? Someone want to say? But if flux is increasing, what? If flux is increasing, what do we know? Then the mag field will be induced in the what?
Opposite of the original one.
Good job. The opposite direction of B original. Okay, and B induced is BIND. Okay, so that's if flux is increasing. All right, so we're gonna do that a lot here in 2 seconds. Okay, and then if flux is decreasing, what do I know? Good, in the same direction. The mag field induced will be in the same direction. Good job. So does anyone want to tell me why this happens real quick before we practice this at 10? Like why when the flux is increasing, does the induced magnetic field go in the opposite direction? And when flux is decreasing, it goes in the same? Does anyone know? Yeah. But so definitely that's true because of science. Any other reasons?
Because the induced magnetic field is trying to oppose the change in the original magnetic field.
Good job. Yeah, yeah. So all that's correct, right? Because of science and science. I like, yeah. And yes, it's trying to oppose the change. And why is that? Like that's where the idea of how this all falls into entropy plays out. Right? Is that the universe, it has this thing about it where it needs to be at equilibrium. It has to. And so that's why thermodynamics happens. That's why when it's really hot in your house and you open up the door, the heat escapes. High concentrations go to low concentrations because everything's trying to come to an equilibrium. And that's the same thing here. The system, nature does not want this system to change. And it's like, well, you're playing with the magnetic field. That's me. I can control that, essentially, is what nature's saying. And so as we try to increase the magnetic field, nature goes, no, you don't. And so it develops something to literally not let us. It wants to keep the system at equilibrium. It wants that magnetic field to stay constant, does not want it to change. And then vice versa when it's decreasing. So good job. Good job. And yes, science. It's all, yes. Let's apply this thing. That's what we get. And I got to start recycling slides here. Okay. So now we'll do the worksheet quite, like I said, during the week. We can definitely go back at those if you haven't already worked on them through SI, but they're literally just looking at that hoop and doing different things with it. But he could definitely throw other questions at you. And he hasn't done it yet. He has not done it yet, but I promise you, I know he does. He asked this question because I've seen it, is that like he will ask you about inductors and he'll give you the direction of the magnetic field in the inductor or the current. And then he's going to ask you to use the right hand rule to get he hasn't done it in class yet. You might say, wait, where's that clicker question? No, you'll see it tomorrow or Tuesday. Okay. During the review, that he gives that question during the review. And then a lot of students are like, well, he never asked that before. It's like, yeah, but because you understand induction and what we're about to do right now, you should be able to do what we're doing now for an inductor. Like if it's having, it works off of self-inductance. So essentially, it induces magnetic field in opposite directions or the same direction based off what's going on. So we'll talk about that in a second, but I want you to know that, this topic, he wants you to know it very well. Okay. So we're going to go through a lot of different examples here. All right. So let's start with this one. And you see, I'll be honest with you, like you've seen, we've literally already given you probably every example. I mean, we could draw different pictures, I guess, but in terms of the examples we've given you about every scenario that we could, one second, Diana, that could potentially show up. So we're just going to kind of run through, I think, the most complicated ones. Some of them are really straightforward. You should be doing worksheets through the optics. So he has you're not going to finish the optics worksheet, but you'll definitely be able to draw I think there's like 5 or 6 ray diagrams that he wants you to draw for the optics chapter. So you want to be able to draw those. And again, we can do those in essay if you haven't got them, but those are and also keep in mind, there are no worksheets for the RLC circuits or electromagnetic energy. So you're not missing anything there. So the worksheets that you need to have for the test are for magnetic force, induction, and then it jumps into optics. So there's not many worksheets. That's also the reason why I didn't do worksheets today, because there's only 3 of them, but there's way more stuff that we need to have to talk about. Yeah, but he doesn't, Rebecca, be careful, because he doesn't have, we haven't talked about, there's a lot of stuff on those worksheets you're going to see, okay? Don't attempt it all, because you won't be able to. Is that 4 through 6? Okay, you all. Okay. The last, like the optics one? Okay, yeah, it should be online, but yeah, just the front one. Hold on. So yeah, just make sure, I can't find it right now, but yes, it's, don't try to do it all, because he asks you a question. There's another question on there where he asks you about 2 lenses. You're gonna look at it and say, oh no, I can do this, trust me. He hasn't shown, there's another equation we haven't even given you. Okay, unless he shows you tomorrow. He does those things sometimes where he'll, and those of you who have had him before, you know that sometimes if he doesn't quite get to a topic, sometimes he'll use the review to teach it to you. Remember, not for heavy things, but he might add one little thing, and that could be something, but I don't think so, because we've only talked, you've been talking about like ray diagrams in terms of 1 lens, but he definitely, based off those worksheets, wants you to be able to do them for 2. And so I don't think he is, but they're not, I promise you, we might even be able, if you want to see what it looks like, tomorrow or something like that, it's actually not hard. So it's not a big deal, but yeah, I don't think he is. Dr. Dungana likes to, like I said, believe it or not, like I don't think I've met another professor that is so concerned about like he's not, I mean, he wants you to understand physics, but the way he has this class set up is for your future. So he doesn't want, if you put in the work, he doesn't want this thing, you're going to get a good grade in here, because he doesn't want this thing to be a burden on your transcript. Okay, so he's trying, he doesn't want to surprise you with things neither, for the same reason. He's just like, oh, here, do this. He's not that type of professor. He's like, no. I want you to just enjoy yourself, learn, and if you work with me, we'll both be happy at the end of the semester. That's Dr. Nagana's philosophy. Okay, so we have this, essentially we're pulling this hoop through this magnetic field here. Okay, so what do we see first? Is there, let me ask you this, where, let me label these. One, we'll call that position 1, position 2, position 3, position 4, and position 5. Looking at this system, are there, because all we're concerned with is induction here. We want to see if there's going to be any current induced in this coil. So are there any pictures that we can already look at this and say, well, I'm not concerned with those, because I know based off the concept that, there's definitely no induction going on there. Okay, good. 3 definitely. And the reason why is like, we can imagine the coil was there and then gets to here. Well, there's 4 in it before, there's 4 after, even here, right? So if there's constantly 4 magnetic field lines in the center as it moves, there's no change in flux. So there's definitely not going to be any there. And then good, yeah, and then the outside. So we know, right? Great. And that's all based off a concept. Here we know there's no B. No B, we can't, like the change in flux has to be equal to 0, right? No B, change in flux has to be equal to 0. We don't have to go any deeper, right? And then in the middle, there's a B, but B is constant. It's not changing. Area is constant. It's not changing, and there's no angle to even play with here. But if we want to put it, there's nothing going on there neither. Okay? We could say it's. I don't like to put the word constant. It's not even there. Okay, so if these are constant or not even present, there can't be any change in them, right? So because of this situation, the change in flux has to be equal to 0 automatically. Does that make sense? If it doesn't, please say like, no, like what? Okay, I'm getting a good response. I am going to slow down a little bit here because this is the most important stuff. I think This is going to be a majority of your questions on the test are going to be between magnetic force and induction, because he did not get enough through optics to even like go there really. So this is crucial here. Please let me know if you don't understand something, or if you're not comfortable now, please send me an email. Let's talk about this stuff, okay? Come to the reviews, something. Okay, but we see here for 2 and 4 that now it's hard to see. Like looking at this picture, this stagnant picture, it's hard to see. You have to definitely use your imagination here, right? Because it's not animated, but this thing's moving to the right. So here we can see it's essentially entering the magnetic field, and here we can see it's leaving, right? It's leaving. And because of that, that's why there's a change in flux, right? We're essentially going from no field lines to 2, right? To 2. And then even when it gets right here from the 2 to then the 4, there's also change in flux right there, right? But it would be anywhere beyond that where everything would be constant until it would then exit the magnetic field. Okay, but just as long as there's a change in flux, if you go from 2 magnetic field lines to 4, that's also a change in flux. Just like right here, when we go from 4 to 2, that's a change in flux, and also going from 2 to 0 would also be another change in flux. Okay, so going from 0 to 2 is a change in flux, going from 2 to 4 is a change in flux, going from 4 to 2 is a change in flux, and going from 2 to 0 is a change in flux. Does that make sense what I'm saying? I'm just using numbers right now, but okay. Okay, because that's how we want to think. We want to imagine this change in flux, see how it's occurring, make sure we understand how it's occurring. Is it the amount of field lines that's in there? What is going on here? So essentially, it's the area that's changing here. Okay, the change in flux here is due to the area that's interacting, because the magnetic field strength isn't changing here. And trust me, we could also say that as you get closer to the center, the magnetic field strength. Let me ask you this. What if I did say that? What if I said as you got closer to the center, B increased? Then what would that mean here? How would things change? Like based on the things that we've already said, would we have to change anything that we have said? Yeah, good. Yeah. If B is changed, right? If it gets close, larger towards the center, we'd assume it starts decreasing also as well. So B would also be changing. So here, right out here, if B was also changing, there would not just be a change in A, but also a change in B. But in the center, we would actually also have a change in flux due to change in B if we were increasing, if B was increasing as we got towards the center, right? So you want to think like that. Like, it's not just like, you don't want to sit here and say, oh, it's just because the field lines are changing, and that's always going to be the answer to this question. No. Even if the field lines weren't changing and we were just turning B up or down here in the center, that would be enough for flux to also occur in the center. That's not what's happening here, but just throwing out these scenarios for you so you're really thinking and you're really, acknowledging when there's a change in flux and when there's not. Like, it doesn't just occur from one thing. Okay, it's several factors. All right. So what is the flux doing in number 2? Is it increasing or decreasing as it enters? Good. I just want to write this more appropriate for you. And there's no change in angle, so we're not concerned with that. So it would really be change in flux equation. Really be, you could write A first, but just B times delta A, right? And the same thing over here. It's the area that's causing the change in flux, right? And then, if you used Faraday's law here, that's what it would look like. Okay, and then you would want to associate this delta T only with A, because the B isn't changing. Okay, so that rate of change is only occurring with the A. Does that make sense? He did this. He explained this to you in class. I just want to make sure you understand that. Cool. Okay. It's pretty straightforward, right? Like, why would you put delta t under B? Like, it's not changing. So there, I mean, you can, but delta t would be, there's no rate of change for B here. It's only A. Okay, let's move forward. All right, so we said increase. Good job. The magnetic field is increasing. So what does that mean about? Now we're skipping. We're going to talk about all the details here, but I want to first do it the way you should be doing it for the test. So we know flux is increasing. So the first step is look at how flux, and this is for any problem, is changing. Like, establish it. Look at how flux is changing. And that also doesn't mean just like change in A or something like this. That also means like ask yourself, is it increasing or decreasing? That's actually the most important part for Dr. Ngana. Okay, so look at how the flux is changing. Is it increasing or decreasing? That's your first step. The next one is to, remember, we're trying to get direction of current here. Good, Levi, is we want to apply Lenz's law. There's more details here, but this is to get this answer on the test and to get it fast. This is how you do it, okay? Apply Lenz's law. So Lenz's law tells us that if the flux is increasing, B should go in the opposite direction. Does everyone agree with Levi there? So that's applying a Lenz's law, right? We ask her, so opposite direct flux is increasing. I don't know what other, you can put other details here. I don't know what other details to put there under Lenz's law. Because you're essentially still applying this idea, but it's increasing. Magnetic field needs to go in the opposite direction. So what does that mean I have to do? Yeah, go ahead, Levi.
Could I just write the generic equation for flux and then just say is increasing, and then because of the original equation or whatever?
You're really breaking up there, Levi. I didn't catch that last part. Hello?
Hello?
Yeah, you're breaking up there, my friend. What did you say there at the end?
So could I just write the generic equation AB cosine theta and then say that area is increasing because delta AB cosine theta flux is increasing or something, instead of writing down the flux equation every time?
Well, I mean, we're not going to have you necessarily, you don't have to write the equation down every time. I'm writing it for you to represent it. But if you're looking at the flux and there's induction going on, then you have to look at the rate of change in flux, right? You can't just look. Am I answering your question?
I guess, yeah.
Let's talk afterwards, Levi, because I want to make sure I answered that. But I think you're asking a kind of just a clarification question for yourself. So, in terms of writing this equation, if there's change in flux going on, you need to always write it in terms of the type of change in flux that's occurring. But maybe you're saying something else. Let's please discuss later. Please, Levi, don't let that go. You remind me when we're done here. Okay. And then after we apply Lenz's law, that's where we use the right-hand rule to get current direction. Okay, so we look how flux is changing, apply Lenz's law, and then we use the right-hand rule to get current direction. What right-hand rule am I using to get current direction? Yeah, well, I know it's hard to remember, but the right-hand rule for the mag field for a coil with current, right? Because if now remember, I told you can do these two different ways, right? You can do, you can use the current to find the mag field, or you can use the mag field to find the current. So in this case, we're using the mag field to find the current. All right. Now remember, the mag field is thumb direction. This is all you got to remember from this. Mag field is thumb direction. Finger curl is going to be your current direction. So that's what we got to apply over here. So since flux is increasing, we know the magnetic field needs to go in the opposite direction. So which way should my thumb be pointing? And again, we're still just talking about position 2 here. Which way should my thumb be pointing if the flux is increasing? And my thumb direction that I have is going to be the induced magnetic field. So if I know flux is increasing, and I'm using the right hand rule where my thumb is going to be the induced magnetic field, then it needs to be pointed in the opposite direction, good, which is out of the screen. So right now you should have, your finger should be or I'm sorry, your finger should be, again, flat, like, extended, like we start all right hand rules, with your thumb pointing out at you. So again, your fingers pointed towards the top of the screen, flat, and your thumb pointed out at you. And now, once your thumb's in the proper position, just curl your fingers. Which way do your fingers curl? Clockwise or counterclockwise? Good job. So that's direction of current. Okay, so I is counterclockwise for this. Cool. Do you see how you get that? Okay. Now do keep in mind, I'm just going to show you. We've talked about this in SI, okay, but I gotta kind of need some room here. So remember, the whole process works like this, though. Okay, it's harder to show in hoops, okay, but it's easy to show in these square coils. Is that at first, what happens is that there's an FB that pushes up on the positive charge and down on the negative, right? Because of the way this is moving, essentially the wire is holding the charge. So that's the direction of V for the FB for the right hand rule. So we see that if our fingers are pointing to the right, our palm is faced towards the screen, our thumb is pointed up, which is the direction of the force on the positive charge. And we know negative would be opposite of that. So this is our electric field that we have set up, right? Or essentially the potential, the induced, maybe a better way would be, that's E induced right there. Okay. And then we get current from that. So that right there is I induced. Right? And it's moving from positive to negative, just like we'd expect. And then B induced, if you were to curl your fingers, like use the right hand rule where you put your thumb in the direction of current, right? We see the magnetic field for the induced current, right? Goes in. It would be right here, it would be pointed down, right? So it would go in here and it would be pointing out on the inside. Or see, it's in the opposite direction. So it proves induction, right? Even if we didn't know Lenz's law, if you went through the whole force situation like I just did, you would still end up with the same answer. Like you would just get the direction of the potential or the direction of the electric field, the way the electric field sets up, draw the current, do the right hand rule for that current, and you'll still end up with the correct answer. But we want you using Lenz's law. I'm just showing you that because that's essentially what we've been doing up to this point. You might be saying, why the heck did we learn about all that stuff before these chapters if Lenz's law is just using the, why didn't we just learn these right hand rules at the beginning? Because why this occurs is because of all the things we've talked about to this point. FB being applied on the charges in the wire, those charges setting up an electric field, that electric field then setting up a current within the wire. Okay, just like that. That's all based off everything we've been talking about. Okay, now for position 4, I just wanted to say that once. We're never going to mention that again, but you should know there's equations to go along with all that too. But Dr. Ngan is much more focused on you just being able to apply these right hand rules. He may ask you an equation or two, but trust me, that'll be the easy part. And this should be easy too. Nothing should be too bad. But what about for position 4? Again, follow the rules on the bottom. So we know there's a change in flux due to a change in area. Is it increasing or decreasing?
Flux is decreasing.
Good, because it's leaving, right? The less and less magnetic fields. Okay, so then what does that mean about Lenz's law? What do we know?
B induced is going to be the same as B original.
Good job. And if you have to, go ahead and draw it. Like put B so that you know sometimes we need to see that B induced to put our thumb in that direction. But you know, if you don't, just naturally our thumb should be in the same direction as B original. And so which way, once you put your thumb in that direction, which way do your fingers curl? Clockwise or counterclockwise?
Clockwise.
Good job. And this also agrees with what we should see. So this is why AC current happens the way that it does, right? Do you see this as an alternating current? Right? It's one direction over here and it's going the opposite direction over here. This is an AC current here that we've induced. Okay, and this is how it happens. So in generators, this is how it happens. If you're like, how does a generator switch the direction of the current? It's sitting right in front of you now. Okay, we can see that the current switched directions based off what the flux was doing, right? And that's all it takes inside a generator. Cool beans?
Hey, Carl.
Mhm.
Is that arrow still in the counterclockwise position? I thought it was clockwise.
It is.
Okay, cool.
You're like, wait a minute, Carl. That's still the same direction. Yeah, my bad. Thank you so much, because I definitely wanted that in the correct direction. Thank you. Okay, cool. Everyone good with that? Cool.
Yes.
Okay. Let's do some more. Now, like I said, I'm not going to get into any of those details. Everything else, we're just going to be practice. Just applying those three, the three things we have on the bottom there. Okay, so what if I then have things tend to get a little bit more tricky. So I have this, and I have this hoop. Now we could do this either way. We could pull the magnet through the hoop, or just like last time. Let me draw this a little bit smaller because I'm not going to be able to show what I want to show. Or we could pull the hoop over the magnet. Either way, it's the same situation. So, right, let's say that there's this hoop and it's really far away. And then it gets closer on it. And then it's really far away again. Okay, so let's just move the hoop. It really doesn't matter, but let's just move the hoop. So let's say the hoop, right, we're pulling it this way. So, and this is very far. So these right here, position 1, position 1 and 5 are, think of them, you know, at infinity. They're very far away. That might be like far away. Where position 2 and 4 are right there. We're going to do one thing that we didn't do last time that I'm going to show you that's going to help you solve these problems. But this is, I just want to make sure everyone understands the situation. So 1 and 5 are very far away from the magnet in the center, where everything else is basically right at the magnet. So first, just like we did last time, because it saves a lot of time, is there any positions here? Because and also keeping in mind that his question is always going to be in these situations, what direction is current? I mean, he might ask you direction of magnetic field, maybe, but you know, usually he's asking, definitely on the worksheets, that's all he asks you for. He doesn't ask you for anything else. His direction of current. But which ones do we not have to pay attention to here? So 1 and 5, they're so far away, right, that there's no the change in flux for these is going to be 0 because they're so far away, the magnetic field's not even interacting with them, right? And then 5, now that's a concept, Dr. Gungana, because I mean, it's important, and he would have talked about it if he was going to test you on it, like it was crucial for that importance. It's just important in terms of physics. But for these magnets, like right here, it's only right here in the center, they essentially have this like constant like it's actually straight and it's constant, so it's not really changing. So you know, even if it's just a bar magnet, when you're essentially on the magnet, there's not going to be much of a the flux won't be changing. We can essentially say that the net flux is changing. Like B might be slightly changing, but not enough. So also here for 3, the flux would be equal to the change in flux. There's flux, just no change in flux. Out here, there's literally no flux, but in the center, there's flux. There's just no change in flux. Cool? Everyone good with that? So 1, 3, and 5 we're not concerned with. It's really 2 and 4 that we need to find the currents in. So the first thing you should do before you try to answer anything here is draw B original. Just because we didn't give it to you. Now again, Dr. Ngana loves you all very much, so he gives you much more than the average physics professor would. But the magnetic field, if he happens to not give it to you, draw it. So what's the magnetic field look like for the bar? It comes out where and goes in where? Just tell me that. Does it go in the north? Or does it go out of the north? We'll see that in a second, Levi. I'll show you. I'll show you. So keep this in mind. And again, this is I trust me. I totally. I'm not laughing at you. I just like every time I hear you all say those things, it just reminds me of me. Like I remember, like seriously looking at this stuff going, I don't even know anymore, man. I thought I knew, but based on everything today, definitely. So no, I trust me, and we all go through these things. So you're not alone at all. Yeah. So this picture actually always like we should be drawing this picture probably more for you because I mean I know there's a lot, but this is like how a generator works. Like there's a plate in here, but this really lets you see the direction of the plate's not important. This really shows you the direction of the magnetic field, right? Like how it works. Like this is just like if we were to put a positive charge and negative charge, like this really lets us see the direction of the electric field, right? So that's the same thing here. And so it always leaves the north and always goes in the south. And oh no, it's okay. Yeah, no, and it's hard. And then I think what's confusing is that because for the earth, right, the poles are flipped, so north, but that's the south pole of the magnet, right? And I think that's where I think things really get confusing because I think you learn that like that's something that sticks in your head. It's like because you know when you learn that you're like, oh man, I never did like north is actually the south end of the magnet, which is why the compass works the way it does. It tells us north, but only because that's the south end of the magnet that it's attracted to, right? So the south is at the north pole and the north is at the south pole. So, but these are exiting. So what I mean is you want to draw them. Okay, so they're coming out of the north and they're going into the south. So you want to do the same thing. Yeah, so you'll definitely see with this picture once we have it drawn that essentially I wanted to put those at infinite, but I hate using that word because sometimes that can be confusing to you, and I don't want to use confusing words. So I just said they're so far away that magnetic field's not touching them for 1 and 5. Okay, that's what I meant by far away. But the reason why you also need to know it's far away is because what you need to know is that from position 1 to position 2, we've gotten much, 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 much closer. And that's very important. Okay. So the first thing you need to do is draw these magnetic field lines if we didn't give it to you. Remember, this is B original that we just drew. Okay. And now we can do everything. right? So we know this wire is moving to the right, right? We just want to apply these rules. Remember, we're just, oops, not those. Well, those, but this bottom thing is what we're doing here, right? This is the induction rules here. We're applying Lenz's law and stuff like that, right? So for position 2, the wire is getting closer and closer to the magnet. So what does that mean? Flux is doing what? Remember, that's the first thing we got to establish. Is if there's a change in flux, and if there is a change in flux, is it increasing or decreasing? So we said that 2 and 4 have a change in flux. Now we're trying to establish if they're increasing or decreasing. Good. And it's increasing because it's getting closer, right? Closer and closer and closer, right? Which essentially, what's changing here?
Is it how many of those magnetic field lines are like being housed in that area?
So it could be, but like based on our orientation, probably from like here to like here, there's going to be probably the same amount of field lines. You see what I'm saying? So
Yeah.
that might be the case for further away. That is definitely something. So what you just said is a very important thing to know. But when we're this close, since there's the same magnetic field lines, there's still a change in flux, because as we get closer to the magnetic field is going to do what? Exactly, get stronger. Remember the question before this, you might be saying, how come that didn't happen with this one? We were never getting closer to the magnet, right? We were essentially like moving in front of the magnet, but we weren't getting any closer to it, right? We were just moving, we were keeping the same distance, just kind of moving in front of it. Where this question right here, the thing's actually getting closer to the magnet, right? So as the wire gets closer and closer to the magnet, as it moves to the right, like B is gonna, not only are there be more field lines as you get closer and closer, but eventually the field lines are gonna max out, but B is gonna continue to increase as you get closer and closer and closer. Does that make sense? So you could definitely say change in A, change in B far away, but as you're close, the change in flux really just comes down to the change in B. But it's both until you get really close. Okay, and that's absolutely true for over here as well. Okay, it's due to the change in the magnetic field again, but once we get further away, the area also becomes a factor. Okay, so it's increasing, magnetic field is to the right. So which way, if current's going to induce, does our induced magnetic field need to be? For position 2, we're just talking about position 2. So we said for position 2, the magnetic field is, or the flux is increasing. So because the flux is increasing, Lenz's law says the induced magnetic field, or essentially the magnetic field that we're going to be showing with our thumb, should be in the same direction, or no, we said it's increasing, right? For 2, it's increasing. It's increasing. So our thumb, which is going to be what we're going to use as the induced magnetic field, good, needs to go in the opposite direction because it's decreasing. So which way should my thumb be pointing right now? Good, absolutely. So to the right, you're opposite of B. Yes, that was great. Sorry. I mean, you gave the answer. I was looking for a different one, but I didn't ask that question. Yes. Thank you. Yes. I'm sorry. Okay. And then, okay, so now remember, it was about an hour ago, but remember what I said about the 3-dimensionality that you have to keep in your head? Well, you need to do that now, right? Because essentially there's this hoop, there's a back to it and a front to it, right? So as we curl our fingers, we got to make sure that our hand is actually directly correlating with the 3-dimension of this hoop. So with our thumb pointed to the right, my palm is facing me. Your palm should be also facing you, and your fingers should be extended towards the top of the screen. That's how we're starting. Okay. Now just curl your fingers. Just naturally curl your fingers. Which way do your fingers point at you? We'll get there. Just 1 second, Rebecca. Just 1 second. I'd like just 1 second. But I like where you're going. So yeah, there's a few things, right? So it's going to be out on top, right? So on top, it's going to go out. That's the current direction. What about in front? Oh, I don't want to do that in blue. What about in front? Which way is the direction going to go here? So right here in the front. Yeah, down, right? You might not know front yet. So now you know. I'm sorry. I'm seeing. I apologize. But yeah, that would be the front, right? But you can see it with your hand, right? Remember, your hand is showing you the three-dimensionality, right? So when we start this thing, the first thing we're going to do is curl the tips of our fingers towards us, right? And that's what this is showing us. That's the direction at the top of this hoop, right? And then we continue to curl our hands, and now our fingers start to point down, which is going to be the direction of current in the front. And then what about at the bottom? What direction is current going to be? Good, in. And then in back, what direction is it going to be? Up. Good. All right. Is everybody getting that?
I want to clarify. Is this B original?
We're using, and so be induced, your thumb should be pointed in that direction. It should be in the opposite direction, and your fingers should be able to curl this way.
Okay.
Does that make sense?
Yeah.
So your thumb's in the, oh, go ahead.
So B original is just where those blue magnetic field lines are, and your thumb would be pointing to the left.
No, B original is to the left, but since we said that there's an increase in flux, that means that B induced needs to be in the opposite direction. So our thumb needs to point to the right. If B original is to the left, our thumb needs to point to the right. So you want to point your thumb in the direction of not the blue B original, but the green B induced.
Yeah.
Okay, cool. Yep. And then once you do that, curl your fingers, you should be getting everything. Does that make sense? Good. Everyone? Okay, cool. And you're asking great questions. Okay, and now I am not joking. The next answer comes by the way we ask you. Okay? Because what if Dr. Dungana says you're looking at it from over here? Okay, so that all matters. And if he doesn't specify, then you ask him. You say, Dr. Dungana, you're asking me to find the direction for current for this hoop, but you're not telling me which way you need me to be looking at it. Because if I look at it over here, it's a completely different situation than if I'm looking at it over here, right? I could be asking you the direction of position 2, but be looking over at the opposite end. He could totally do that. That's how we make these questions really challenging. Is saying, yeah, but what's it look like from on this side, right? So always make sure, and he will tell you which way to look. But if he doesn't, you need to find out, because you can't give us a direction unless we tell you which way you need to be looking at this thing. So looking at it the way we have it, right? This is the eyeball here. Which way is the current moving? Clockwise or counterclockwise? Good. Clockwise, right? And if you're not sure, curl your fingers and literally tilt your head to where your eyeball would be in orientation to this picture. Like, look at the way your fingers are curled. Tilt your head and watch your fingers curl with your thumb in the direction of B induced. You'll see that it's twisting counterclockwise based off the way we're looking. But what if we looked from the other end? Again, do the same thing. Just put your head at the other end. Now you're looking at your thumb, and you're seeing what? Counterclockwise, right? So it's all based off the way we ask you. Okay, so make sure you can do it, right? It's hard to give an answer from this side, right? Let's just say from this side. I don't want to make things too complicated here, right? It's clockwise. That's the direction of current. Okay, cool. And that's how you do it. And keep in mind, once you have this like idea of 3D orientation, like, you can look at, you just use that to your advantage and look at it from the way we're asking you to look at it. Like, don't try to make it hard and be like, what would it look like from that position? No, you could literally put your head in the position of the way we're asking you to look in terms of orientation to your fingers, the way that they're curling, and see everything you need to see. Right? And what about position 4? Good. Flux is decreasing. Decreasing flux. So what does that mean? Yeah, let's keep the same position. So we're still looking from over here. Because if we switch it, then the answer is going to look the same. Good. B induced is in the same direction as B original. So now we want our thumb in the same direction as the blue magnetic field lines, right? Good job. And then we want to curl our fingers. So what direction is it, the current at the top? With your thumb pointed to the left, go ahead and curl your fingers. Good. In, and then the back. Good. Down. And then the bottom. Good job. And then the front. Good. And go through this process. Don't make it a guess, okay? You see how you can see all these things, huh? So you can do this on the test, and don't make it a guess, and you know, go through the steps to make sure that you're right. It's worth it. It's worth it. All right. So based off, again, the keeping the same position, so looking at from the left side, looking from left to right, what direction is current for position 2? Good, counterclockwise. And again, that's what we should be seeing. It should be in the opposite direction over here. Flux is decreasing versus it increasing on the other side. Again, AC current, right? Okay. Did you want to run through any more of these? I mean, we can do all kinds of crazy things here. Okay. Okay, but if you need more, and like I said, we still have 3 more days to practice this. Okay, this is just, the initial review. But Monday, Tuesday, Wednesday, we are going to be, definitely, we could practice this a ton more. Things like this. So remember, just going back, right? The questions he's going to ask you are the ones he's already asked you, right? So he definitely asked you this, right? He definitely asked you about this, right? So you want to know the questions he asked you. Like if you're like, what other scenarios could he throw at you? All the ones he's asked you. Which ones wouldn't he throw at you? The ones he has not asked you. But also keep in mind, when you look at the worksheet, that's really going to show you what he's wanting you to see. Okay, he literally just uses the same picture for all 7 questions and just changes what's occurring. And just as long as you can flow with that worksheet, you're going to be good, because you're going to be able to do everything that we want you to do in terms of induction and the right hand rules. But remember, the other thing that he could, but I don't know. See, this is where you have to go back and look. I'm not looking at, I can't see all his questions in my head right now. But, you could also use this right-hand rule to find, he might just ask you which way being, keep this in mind. Even though we were finding the direction of current, he might just ask you for B induced and you're done. Let me say that. You might not, maybe on the test, he might not have you go all the way through current. Sometimes he might just say, hey, which way is B induced going to be? Or he might ask you 2 questions. Which way is B induced? Then which way is the current? Right? He could give you 2 questions for one picture, stuff like that. Okay, so don't think it's always just the current, but the only other thing he could really ask you to find is B in terms of using the right hand rule. Okay, but everything else could come through the mathematics, right? The different equations that apply to this stuff. Okay, so let's move forward. So induction, right, implies 2 inductors. Like I said, we'll probably have to practice this more, because he's not going to do it a ton, but there will be one question that has you do this, where you're actually using these right hand rules that we just got done practicing to get the direction of like induced magnetic field or induced, you know what? Let's do that. Let's do that one, because based off everything we just did, it's all fresh in your head. You'll actually be able to do this. And if not, it's okay. Okay, but he hasn't done this to you yet. He will do it on the review though, I promise. So you might have this inductor. Inductors are just coils. Okay. And he's going to tell you the direction of current. So like in this case, that's the front and that's the back. Okay, so this is the front. This is the direction in the front. Like I can't do draw it very well, but that's the current in the front, and this is the current in the back. Okay. So the first thing you need to do from this, when he says, okay, this is the current, the first thing you got to do is get the magnetic field from just the current, not the induced, just the magnetic field for this. Does anyone know how to do that? Remember, we talked about all 4 right-hand rules today already. It has to be one of those right-hand rules. Do you know which one it is?
Just like putting your right thumb in the direction and seeing how your fingers like curl around it.
Well, yeah, we want to, in this case, you're right. That's the right-hand rule. But in this case, we'll be doing it backwards, right? Where we'll curl our fingers and see where our thumb lands up. Before we were putting our thumb in a direction and seeing what our fingers do, right? It's the same right-hand rule, right? We can just do it interchangeably. Exactly, my friend. Exactly. That's the one we want to do. Good. Exactly. So in this, like I said, I can't do 3-dimensionality, but please pay attention to the words I'm using here. So currents in front is going up, the current in back is going down. Okay, so you want to start this by your palm should be facing the screen, your fingers should be pointed towards the top of the screen. You're essentially trying to mimic the front current direction here. So it's going up. So you want to start your hand in that direction. And then just so your fingers are extended up and your thumb, like I said, for all right-hand rules, should be perpendicular to your pointer finger, which means your thumb should be pointed to the left. Now here, just curl your fingers, right? Now that your hand is in the proper direction, you can just curl your fingers because it's going to follow the direction of the current through this coil, right? So in back, it should be pointing down and your fingers will point down as you start to curl your fingers. And your thumb ends up in what direction? To the left or right? When you do that. Good. So this is B original. All right. Now, what he's going to say, you have to do that first. He's not going to ask you to find B original, okay? But you have to do that first. And then what he's going to ask you is like, what's the direction of B induced or what's the direction of I induced? He can actually ask you either one of those, but we have to get both of them anyway. So once you have that, and then he tells you that the current, he would have to give this information, okay? He would have to tell you the current is either increasing or decreasing. So in this case, current is increasing. Current is increasing and moving in the direction that we have. So what does that mean about the flux in this inductor? If current's increasing, what does that mean about this magnetic field and the flux that's going on here? Good. So remember the area of this coil is actually establishing our flux. We talked about that. The conductors always establish the area for the flux. So the magnetic field is moving through the center. Go ahead, Levi.
Wait, what are we comparing the initial current? What is the initial current that we're comparing this current to?
We haven't talked about any other current. This is the initial current. This is the current running through the system at the time. So that's the only current we have so far. We're going to get another one, but we haven't talked about the induced current. This is like the original current.
So why is the current increasing? Is this like when a switch has initially been turned on or something, or
well,
what is
that's
this simulating?
No, that's definitely one spot, Levi, but where your head should be, where all of your head should be, is AC circuits. Because AC circuits, current is constantly increasing and decreasing, right? And that's where we're going, right? We have to talk about those RLC circuits. And so like current, right? It's constantly changing. So the current in that inductor will also do this. It's going to go up and down, up and down. And that's actually what an inductor does for a system. The inductor tries to keep the current stable because the current's going up and down. And so the inductor is like constantly changing its magnetic field and then constantly changing its direction. It's induced magnetic field to compensate for the change inside the RLC circuit because it's oscillating, right? That's what's going on. It's a huge picture. It's such a big picture, but that does that make sense? It's more about the EM, because all these inductors, and that's what we talk about in this class, is this inductor being in an AC source, right? So that now this is an inductor, right? Potential and current are by the way, an inductor, just we're going to talk about it here in 2 seconds, but who leads and lags? Let me do it this way. It's that. So potential leads the current. And why? Because of induction, right? I'm not going to have this induced current without a potential first. So potential has to lead the current. It has to come before it. Where in a capacitor, the capacitor doesn't have a potential without the current, right? The capacitor needs a current to have potential. So current leads potential in a capacitor, right? That's where those things are coming from. So the reason why we say potential leads current in an inductor is because of the actual process of induction. You need an induced electric field to have an induced current. Okay, so he's going to tell you this. He's going to say current is increasing for this particular situation. So which way should my thumb go if current's increasing?
Sorry, how would I know that current's increasing just from?
I just said, Levi, he's going to tell you. I said
Okay.
Okay, so good. Yeah. So it should go in the opposite direction of the original, right? Because it's increasing. Good job. So our thumb should be pointed to the right, right? So B induced is going to be this way. That could be one potential. And remember, it's not always this way. If you said current was decreasing, which way would B induced be? Good. Keep that in mind. He can give you any scenario, current increasing or decreasing, okay? Good, but for this one, current increasing, B induced opposite direction. So what does that mean? I think he just asked you for B induced here, but the current's going to go which way? The same or opposite direction as the current in the inductor? The induced current. I forgot to say that. The induced current is going to go in the same direction as the original current. Good. Opposite. Good. Right. And if you need to know, remember, we're literally just using the same right-hand rule over and over, right? So to find that answer, put your thumb in the direction of B induced and just curl your fingers, right? You can see in back it's up, right? Where for the original current in back it was down. But our induced current in back it's up, right? And in front, the induced current is down. So it's in the opposite direction, which it should be, because that's what an inductor does. Like I said, it tries to keep the current constant. So as the current tries to increase, the inductor produces a current in the opposite direction because it's like, no, you can't go up. You have to stay constant. And so that's the point of an inductor and what it does in the system. But he's definitely going to have you make sure that you can run through that entire concept in terms of the right-hand rule. Now, RLC, so everyone good? We're going to move forward to RLC circuits.
Does this use the second Faraday's law equation? How does current relate to flux? Is it N flux equals Li? Is this self-inductance?
Yes, this is self-inductance. So there's two different equations, right? But you have them on your equation sheet. So this is self-inductance, and that's the one you'd want to use. You'd want to use the flux for self-inductance. Yeah, I think it's Ly. I can't remember off the top of my head, but yes, it's on your equation sheet. He literally labels it for you. Cool. He labeled, by the way, a lot of the equations are labeled, but he doesn't give you all of the equations, but a lot of the equations that are on your equation sheet I know are labeled to the specific, which is nice for this section, that's for sure. Okay, ready for RLC circuits? Okay, so here, believe it or not, we actually want to start with our original idea of circuits. So this RLC, because when we say, and trust me, Dr. Ngana said this, but he kind of, again, there's no worksheets for this section. So the only questions you really got to know for the test is anything he might give you on the review or the questions he gave you in the lecture slides. There's not many questions even for this section. Okay, but if you need to answer a question from this section, you need to remember all the things that you knew from circuits, which is how he started this section when he was explaining it to you. And so these are RLC circuits, but not just RLC circuits, they're series RLC circuits. That's a very important thing because we wouldn't be able, the things that we're saying in this chapter, we cannot say if they're not in series. Okay, so what do we know about series? First of all, we know that in series, are resistors directly added or are they inversely summed? Good. And so that's going to be true here. Now, remember, you've talked about a lot of this already. Remember, the inductor and the capacitor have this thing called reactance. The reactance works as the resistance. Okay, it works as the resistance. And if we can get into the details of that more if you want to, but that is not something he's testing you on. Okay, that's just like a cool thing we could talk about. But it works. It's what all you need to know in your head is that reactance works as why did I erase everything there? Reactance works as resistance. So essentially, if we were to get resistance here, we just have to directly add them. But what do we know? And that's what we do. We do it using Pythagorean theorem because they're not in phase with each other. That's why we have to use Pythagorean theorem. But for Pythagorean theorem, when we get the total resistance of the system, that's what we're doing, right? R squared plus XL minus XC squared, right? So this is the resistance of the inductor and capacitor. This is the resistance of the resistor. We're just adding them together. The only reason why we're using Pythagorean theorem is because they're not in the resistor, the inductor, and the capacitor they're not in phase. Their currents aren't in phase. Is there a question?
So does XC or does XC slightly cancel out XL because they're out of phase?
No, they never cancel each. Like they're going to be in different direction. I mean, I guess like you want to. I guess you can think that way. Yeah, I guess that's
XL
fine.
minus XC.
That's fine. Well, it's only that because of the vector. So Z is impedance, and it's just the total resistance. Impedance is just the total resistance. It's the impedance to the flow. That's what it actually is, because that's what an inductor and capacitor are doing. Like the current's coming and it's fighting it, so it works as resistance, so it impedes it. And the XLXC, remember that situation's coming from the phasor diagram, right? So when we look at the phase of the resistor, the inductor, and the capacitor, we see what this means when we write this is just R. But when we write that straight across, that's trying to say that it's in phase with the system, which is the source EMF. And then, and trust me, XL does not always have to go up. I don't know if Dr. Ngana does this to you, but he may, like XC can, or I'm so sorry, XL can totally be down and XC can totally be up, right? Because if you're looking at the system at a certain point where the inductance is increasing in the capacitor and the reactance is increasing in the capacitor and the reactance is decreasing in the inductor, which would be where the current is either increasing or decreasing, then you got to draw them appropriately. See, if the inductance, reactance in the inductor is decreasing, then it needs to be pointing down. That's what that means. It's decreasing. And if the inductance in the capacitor is increasing, it should be pointed up. But if the inductance in the reactor is increasing and the inductor in the capacitance is decreasing, then they need to be in opposite directions. So this could be, right? Let's do this. Is that, you know, when we net this, like try to get total impedance, like for this one, see, this would be XC minus XL, right? Because if I were to get the total here for this vector, you know, you might have, you know, XC minus XL be the case for this. Okay, this could also, if XL and XC is one's larger than the other, then this could also point in the opposite direction. Oh yeah, it doesn't matter down here. I'm just showing for the, yeah, you're right. I'm just showing for the phasor diagram, but for the impedance, it doesn't matter. You're right, because they're squared, so it doesn't matter. I'm just letting you know that they could be written two different ways. Like it's, you know, it can be XL minus XC or XC minus XL, right? Based off what's going on. And then this net could also be pointed in the opposite direction based off, like, if XC is really small. Trying to erase. So let's say, like, oops. Let's say you know, this is XL and like this is XC and this is R. Well, then when you subtract these two, right, there's still going to be some XC left. So in this case, the end phasor diagram would look like this would be Z, this would be R, and this would be XL still minus XC. We'd still write it that way, right? But it would be pointed down. Does that make sense what I'm saying? So it's based off like the length of the vector in terms of those pictures, but he doesn't do that very much. Like, trust me, there's professors that do, but and that's why I haven't focused so much on the phasor diagrams, because now he may on the review. I can't remember every new question he asks you on the review. So he may have you do this opposite thing on the review. But no, that's how it could happen. It can happen either way based off who's larger, right? And again, if this is larger than this, when we subtract it, then there's going to be, you know, there's going to be some left still pointing up, right? So now this would be XL minus XC, but pointed up instead of down. This would be Z in this case. So based off the direction of the way this is pointing is all based off of like how the subtraction happens here. But like I said, I don't think he goes that deep here. You know the questions he's going to ask you in terms of the lecture slides. Once you have the review, you'll know if there's any other questions that he might choose to ask you about phasor diagrams. But he asked you the phasor diagram where the one question I never see professors ask, where he asked you about how this thing twists. Remember that? He was asking you about like its phase space. You might not have realized that, but one of the clicker questions he asked you, yeah, and we can go over. We don't have time to cover it right now, but we can definitely do it. Like, you know, we have 3 more reviews during the week that we can talk about that. So the voltage phasor diagram is different from the reactance, right? But they're both doing the same thing because they're going to tell us the same thing. So we also have those phasor diagrams where we could look at the potential through the resistor and the potentials through the inductor and the capacitor. And so, and it works the same way, but when we do this phasor diagram, right, depending on how it ends up, I'm just going to generically write it like this. Then when we get the net here, right, this is going to be the EMF, right, the source EMF, and it should be. That was the next thing I was going to show you here. Because of the this is a series circuit, I don't think, again, Levi, you know the answer to that question already, my friend. You do ask me that quite a bit. And what does the answer always end up being? You know the questions he's going to give you already, my friend. They're on the lecture slides. Okay. So if you're like, is he going to ask us a question? I don't know, man. I don't have the questions memorized on the lecture slides. Look, if it's on the lecture slides, then yes. Or on the worksheets, yes. If it's not, no. I can't answer that question with any more detail, my friend. I don't have all his questions memorized. You know? So I don't know. I do this for a lot of professors. I can't remember all the details. Okay, so because, oh man, I just erased a ton of stuff. So because this is a series circuit, right? We know that the total potential is going to equal to 0, right? With the source EMF, the total voltage, the capacitor, inductor, and the resistor. And so what that means is that the total source EMF, and that's what this is trying to tell you with this equation. Okay, is that the amplitude for the RLC circuit is based off the source, right? Because if we were to, well, if this was negative, we'd add it over, right? It doesn't matter. These things ended up being added, and if we subtract them all, it's just like they're all negatives. Based off the signs here, I would have to subtract them all over, but they'll all be subtracted from each other, so they're still being added. So I kind of flipped some signs here so that it made sense to you. But essentially, the source EMF is equal. We know this. This is something you learn for series circuits to the sort. Like remember, we're talking about amplitude right now. We are not talking about the phase. Okay, they're out of the EMF is out of phase of the system by whatever this angle is. That's what we call the phase angle. Right? But the amplitude of the system is directly coming from the source EMF. Right? So if we got to have, this is Kirchhoff's law that we're talking about, but you just need to understand that because that's why you're able to write the equations that you're using, right? So this RLC circuit, looks like this. Well, the source EMF is going to have a certain voltage associated with it, and that voltage is going to be equal to all these voltages added together. Okay, and so because of that, we have this new Ohm's law, and that we can write based off of that's the sum voltage, and then we know what the sum resistance is going to be, which is the total impedance is the sum resistance, which we've already talked about. So these RLC circuits have a new Ohm's law with them, and this Ohm's law describes the total system as a whole, right? Where current doesn't change, so current in the inductor is going to be equal to the current, like the amplitude, right? The amplitude of the current in the inductor, the amplitude of the current in the resistor, the amplitude of the current in the capacitor, they're all going to be equal to themselves in terms of amplitude. Now remember, they're all at a phase of each other. They're not in phase with each other, but they are all in terms of amplitude. And that's all this equation is trying to talk about. It's the amplitude of EMF, the amplitude of the current, and the amplitude of the total resistance of the system. Okay. And then if you have to, if we ask you like how in phase or out of phase the source EMF is with the system, which means we're asking you, how does the current from the source oscillate in terms of the current inside the system, which is oscillating back and forth, right? But the current in the system is oscillating back and forth based off the way the inductor and the capacitor are discharging. So these dictate how the current oscillates inside the system, and the EMF is providing, right, the amplitudes for those things, right? But they might not be in phase with each other, and that phase difference, as you saw, can be written a few ways. but that's what the phi is, the phase difference, okay, not the tan theta. Okay, but the phi, yeah, you can take off if you got to it. We're almost done. I'm going to talk for, you know, the 9 more minutes we have left. And then, like I said, we have a ton of other reviews to have this week. So, you know, anything we didn't talk about, we didn't get to optics, but there's not too much. And we'll definitely do that on Monday. We'll start on Monday with anything we didn't do today or tomorrow. Tomorrow's SI, we'll finish off the review from today. That's how we'll start. And then we'll get into your questions. But here, that tan phi, right, it has an equation associated with it. Yeah, no, I'm definitely going to cover everything. I just, you know, I want to respect your time, and yeah, I want to make sure that, you know, you all enjoy your Sunday. So as much as you can. So this phi is the phase difference. Okay, it's the phase difference. It's the difference in oscillation. If that's not making sense to you, that's okay. Just know that the phi is because this part, he's not really so focused on you knowing the concepts as he is just making sure you understand the math. Okay, so if you know what the phase difference is, when he asks you for it, you know what you're solving for. You may be like, I don't know why, like what this thing is, but I know that phi is the phase difference. Just like the power factor. The power factor also includes the phase, you know, the phase difference between the sort, like that phi, the phi in that tan theta and the phi in this cosine theta, they're the same number. So you can get this number 2 different ways. Okay, if you know like R and Z, you can do like, you know, inverse cosine R over Z to get power factor, right? Or if you don't know R over Z, right? Or I'm sorry, to get the phase difference, not power factor. I'm so sorry. I meant to get phase difference. But if you don't know, you know, maybe R, you know, let's say you don't know those, you could still get the power factor, right? Because the other way you write that power factor, I know I just have it written there in terms of XL, but remember, it can also be written in terms of VL minus VC over VR, right? So you can all, if you just know the potential, you can still get the phase difference. Because up here, it's like, well, I know the reactance in the R, so I would know R and Z, so I'd know the power factor. So I could use cosine phi every time. Yeah, maybe not. But oh, how nice of you, Levi. So if anyone didn't see, Levi did some nice stuff, and I would definitely encourage you all to work together. But looks like he made a little document for you all. And I also have a document I'm going to send you, but it's just for the, you know, it's not, Levi did a lot more work there. I don't see it there yet, Levi, but I'm sure you're going to post it. But I'll send you a document on optics, but it's nothing that Levi has probably provided. So that sounds like he went through a lot of work there. That's fantastic, Levi. Thank you. That is amazing. All right. So I know we're all burned out here, so a lot of this stuff isn't, you know, probably resonating like it was at the beginning, but you know, this is being recorded. It should post, everything should work out fine. So know that, like I said, for these RLC circuits, let me just make this perfectly clear one more time. We're much focused, just as long as you're able to do the mathematics, the concepts themselves. The only concept that is really going on here is the idea of resonance. Like, that's why we bring it up. And the reason why we bring up the idea of resonance here is because of the difference in phase shift. Like, these things are oscillating different, right? Like the inductor and the capacitor might not be resonating with themselves. And if they're not resonating with themselves, then the current, right, is not going to be at its max amplitude, okay? Because essentially the inductor and the capacitor, they're going to be fighting each other. They're, you know, this is going to be discharging the current this way, but then if this is discharging the current that way, the current can't reach a max amplitude within the system, because the inductor and the capacitor, they're discharging in the opposite way, right? But when they resonate with each other, which means the capacitor and the inductor, they discharge that way, and then they discharge this way together, right? So they discharge one way together. they discharge the other way together. And when they do that, that means that they're resonating with one another back and forth. And that's where we get max, like the current amplitude within the system will reach its max, because the inductor and the capacitor are essentially resonating with the source is what they're doing. Like the source has a certain omega, right? That's dictating like what's coming in. And then when these things start essentially resonating with the source, everything max amplitude of the current appears. And so that's why omega, or that resonance frequency that we were talking about, is just due to the reactance and the capacitance of the system. Because when these two things are resonating with each other, are essentially discharging in the same direction at the same time, this thing oscillates at a certain frequency, right? We know omega is 2 pi f. Omega naught is just a special way to write a special type of omega. This is resonance frequency, not just any type of frequency, but resonance frequency. So we write it as omega naught. But it's where is it coming from? It's coming from the oscillation of the current due to the way that the inductor and the capacitor are discharging with themselves. And so when they discharge with themselves, you're going to get something called resonance frequency, and then you get max amplitude. Okay, so that is that, like, you know, that chapter, like, you know, there's a few more things that he talks about, but, you know, he's really focused on, do keep in mind that, you know, because these are, like, I know, remember we there were like equations for you know, the potential as a function of time in the resistor, and the resistor, the capacitor, and the inductor. Dr. Ungana doesn't focus on those so much, but he does want you to know the maxes, right, for all these. And so I just forgot to write them. But know that, like, you know, VC is equal to this, VR is equal to this, and VL is going to be equal to that in terms of equations. Like I said, he just wants you to know equations. And then the reactances you can look up, right? You know, XL is equal to, geez, I don't even know that off the top of my head. The heck is that thing equal to? Omega L, right? and then XC. So that's the last bit of it there. In terms of the mathematics for this equation. Like I said, we're going to pick up from here. So I'll review a little bit of this tomorrow, you know, just in case I missed anything, because I was kind of trying to rush here a little bit to get some stuff in. But we'll start here tomorrow, and then we'll finish off optics. And then it'll be, if you don't have any questions, that's fine. But I definitely would love for you to bring any clicker questions, any worked out questions from the slides, anything like that, to SI. Let's get the stuff answered. Let's make sure you rock the crap out of this test, okay? And I know you all can do it.
Thank you so much, Carl. You're the best.
No, you all are the best, and I'm super proud of you. I'm super proud of all of you. So keep up everything that you're doing, because it's amazing.
Thank you. I really appreciate it.
Absolutely. It's my pleasure. Thank you for coming. Like I said, we'll finish everything tomorrow. But great job today. And if you have questions, please ask away. I'm going to hang out. So, you know, if you have something, you know, ask away. But, you know, please, I don't want to take any more of your time. Go enjoy your Sunday.
Actually, I just remember. Something just hit me when we were doing the magnet one with the north and south pole on the magnets.
This one?
Yes. Wait. Yeah. So 1, 3, and 5, those positions, there's just nothing going on. Like flux isn't changing. So we
right. Keep going.
Not that we ignore it, but just, I don't know. Nothing's really happening there. That's why we didn't do anything at those points. I just wanted to clarify.
No, absolutely. So in this case, like, flux is 0 because like B isn't changing. The reason why we had flux here was because B was changing, but the change in B here is 0. So the change in flux in the center is 0. And even out here, the change in flux is due to the change in, oh, I have it written right there, is going to be due to change in B. But out here, this is so far away. Essentially what I was saying is that first, these are going to curl away, and then this one just wouldn't even, because it's so far away, wouldn't even be there. It'd be so faint that it wouldn't even register anything in the hoop. So this one's so far away that there's just, B is equal to 0. There's just no magnetic field there. So the change in flux would be equal to 0. And the same thing here. There's just literally like no magnetic field there. So because of that, the change in flux is equal to 0. Does that make sense?
Yeah, it makes sense. Thank you.
Absolutely. Great question. Great question. Hey, Levi, hold on one sec. Let me stop this recording here. But